Imagine this. A human being is floating outside a spacecraft farther from Earth than any normal rescue could ever reach. There is no wind, no sound, no up, no down, only darkness, stars, and the thin glow of instruments reflecting inside the astronaut's visor. Everything looks peaceful. That is the trap. Space never looks violent until something fails. The astronaut is moving slowly along the outside of the spacecraft, one hand locked on a rail, the other reaching toward a panel. Inside the suit, fans are running. Oxygen is flowing. Cooling water is moving through tiny tubes under the clothing. Pressure is holding the body together. The suit is not just clothing. It is a small artificial Earth wrapped around one fragile human body. Then a warning light appears. At first it is small, easy to miss. A pressure reading drops slightly. The astronaut notices it, but the mind tries to stay calm. Maybe it is a sensor error. Maybe the system will stabilize. Maybe this is just one of those small alarms that happens during complex missions. Then the second warning comes. Pressure falling. Oxygen leaking. Suit integrity compromised. Now the astronaut knows something is wrong. There is still no explosion, no dramatic movie moment, no giant tear ripping open, no screaming into space. Just numbers falling on a display, faster than they should. The astronaut turns back toward the airlock. But space does not care about distance. The airlock may be only a few meters away, but those few meters have suddenly become the longest distance in the universe. Inside the suit, the pressure continues to fall. The body feels it before the mind fully understands it. Breathing becomes strange. The chest feels different. The gloves begin to feel tighter and looser at the same time, as if the suit is no longer behaving like a suit. The astronaut tries to move faster, but every movement in a spacesuit takes effort. Nothing is quick, nothing is natural. Then something terrifying happens. The astronaut feels saliva on the tongue begin to bubble. Not because it is hot, because pressure is disappearing. This is the moment most people misunderstand. They think the first danger in space is freezing. They think the first danger is oxygen running out. They think a person would instantly become ice or explode like a balloon. But the real first killer is pressure. Your body is built for Earth. Every breath, every heartbeat, every drop of blood assumes that air is pressing on you from every direction. Remove that pressure, and the body does not simply run out of air. It begins to physically fail. The astronaut's vision starts to narrow. The brain is still using oxygen, but no new oxygen is coming in properly. The lungs are no longer operating in the world they were designed for. Blood flow is becoming unstable. Gases inside the body begin behaving in ways they never behave on Earth. 10 seconds. That is all it can take before consciousness begins slipping away. Not minutes, not a long heroic struggle. Seconds. The astronaut reaches for the airlock handle. The hand is there. The mind knows what to do, but the body is already losing the ability to obey. The stars remain silent, the spacecraft remains close, and the universe remains completely indifferent. That is the horror of deep space. It does not need monsters. It does not need explosions. It does not need fire. It simply removes the conditions that allow a human body to function. Tonight, we are not going to talk about space the way movies show it. We are going to talk about space the way physics actually makes it. Because deep space is not just empty, it is not just cold, it is not just dark. Deep space is an environment where the human body is instantly out of place. Every system you depend on, your lungs, blood, brain, skin, eyes, heart, even the water inside you, starts facing forces it was never built to survive. And once you understand what really happens, you will never look at the stars the same way again. Part 2. The lie movies told us about space. Most people learned space from movies. A hatch blows open. A character is thrown into space. Their face freezes. Their skin turns white. Their body becomes stiff in seconds. Sometimes they explode. Sometimes they drift away slowly while speaking final emotional words. It looks dramatic, but it is mostly wrong. The truth is far stranger, and in some ways far more disturbing. A human body does not explode in space like a balloon. Your skin is stronger than people think. Your tissues are not paper. Your body has structure. It can contain internal pressure for a short time. You would swell, yes. Your body would expand, but you would not burst apart instantly. You also would not freeze instantly. That one surprises people the most. Space is extremely cold in one sense, but cold does not work in space the way it works on Earth. On Earth, cold air or cold water pulls heat away from your body quickly. That happens through conduction and convection. But space is a vacuum. There is almost no matter touching you. No air to carry heat away. No water to drain your warmth. So your body loses heat mostly through radiation, and that is much slower than movie scenes suggest. So if you were exposed to space, freezing would not be your first problem. You would be unconscious long before freezing mattered. The real danger is not cinematic. It is biological. It is pressure. It is oxygen loss. It is gases leaving solution inside your body. It is moisture boiling from exposed surfaces. It is blood circulation becoming unstable. It is your brain losing oxygen so quickly that your final conscious experience may last only a few seconds. Movies lie because reality is too fast. There is no time for a long goodbye. There is no time for dramatic speeches. There is barely time to understand what is happening. Another myth is that you could survive by simply holding your breath. That sounds logical because on Earth, if you go underwater, you hold your breath. If smoke fills a room, you hold your breath. If air becomes unsafe, your instinct is to seal your lungs and protect what oxygen remains. But in space, that instinct can make things worse. When outside pressure disappears, the air inside your lungs expands. If you hold your breath, that expanding air has nowhere to go. It can tear lung tissue. This is the same reason scuba divers are told never to hold their breath while rising to the surface. Even a pressure change underwater can damage lungs. Space is a much more extreme pressure change, so the natural survival instinct becomes dangerous. That is what makes deep space so cruel. It punishes the body for doing what usually protects it. Another false idea is that space is simply empty. People imagine emptiness as nothing happening, quiet, still, peaceful. But deep space is not harmless emptiness. It is vacuum, radiation, extreme temperature contrast, micrometeoroids, solar particles, and cosmic rays. It is a place where the absence of Earth becomes the attack. Space does not need to touch you with claws or teeth. It only needs to remove air pressure, oxygen, warmth balance, and radiation protection. On Earth, survival feels normal because Earth does the work automatically. You do not wake up and check whether there is enough atmospheric pressure. You do not worry whether the magnetic field is still deflecting charged particles from the sun. You do not think about the ozone layer blocking dangerous ultraviolet radiation. You do not thank gravity for keeping your blood and fluids behaving normally. But the moment you leave Earth's protection, all of those invisible services disappear. That is why space travel is not just transportation. It is life support engineering. Every astronaut is alive because machines are constantly replacing the natural protection Earth gives for free. So before we talk about what space does to the human body, we have to understand one thing clearly. Earth is not ordinary. Earth is the exception. The universe is not naturally friendly to life. The universe is mostly vacuum, radiation, and darkness. The habitable surface of our planet is a thin, fragile layer wrapped around a rock. And inside that thin layer, humans feel powerful. Outside it, we are exposed, and deep space reveals the truth very quickly. The human body is not weak because it cannot survive space. The human body is specialized. It is built for one kind of world, a world with air pressure, liquid water, gravity, shielding, and oxygen. Take away that world, and the body does not become heroic. It becomes physics. Part 3. Earth is not normal. Earth is a life support machine. Before we understand why deep space is so deadly, we need to understand why Earth is so protective. Because the most dangerous thing about space is not what it adds, it is what it removes. Right now, wherever you are sitting, Earth is quietly keeping you alive in dozens of ways. You are not aware of most of them because they have always been there. They feel normal, but normal is an illusion created by constant protection. Start with air. Every breath you take depends on a very specific atmosphere. It has the right pressure, it has the right oxygen level, it has enough nitrogen to dilute the oxygen so the air does not become dangerously reactive. It has enough density for your lungs to pull in oxygen and push out carbon dioxide. You do not manufacture that air. You do not pressurize it yourself. You simply breathe because Earth has already prepared the environment. Then there is temperature. Earth stays within a range where liquid water can exist. That sounds simple, but it is one of the most important facts about life. Too hot and proteins break down. Too cold and chemistry slows. Too unstable and complex life struggles. Earth is not perfect everywhere, but compared to space, it is unbelievably gentle. Then there is gravity. Gravity holds the atmosphere to the planet. Gravity keeps your body oriented. Gravity keeps fluids behaving in predictable ways. Gravity gives your bones and muscles a constant reason to stay strong. Your heart, balance system, skeleton, and blood circulation all evolved under Earth gravity. Remove gravity and the body begins changing. Fluids shift, bones weaken, Muscles shrink. Balance becomes confused. The body slowly rewrites itself because the environment has changed. Then there is the magnetic field. You cannot see it. You cannot feel it. But without it, life on Earth would be exposed to far more charged particles from space. The sun constantly throws out energetic particles. Galactic cosmic rays arrive from deep space. Earth's magnetic field helps deflect many of them, guiding some toward the poles, where they create auroras. Those beautiful lights in the sky are also a reminder that Earth is shielding us from something dangerous. Then there is the atmosphere itself acting like armor. When small rocks hit Earth's atmosphere, many burn up before reaching the ground. When high-energy radiation arrives, the atmosphere absorbs much of it. When ultraviolet light comes from the sun, the ozone layer blocks the most damaging wavelengths. You can stand outside under the sun because Earth filters the sun for you. In space, there is no filter. The same star that gives Earth life becomes a direct radiation source. This is the truth most people miss. Earth is not just a place. Earth is a complete life support system. It provides pressure. It provides oxygen. It regulates temperature. It shields radiation. It recycles water. It grows food. It processes waste. It protects life from most space debris. It gives biology a stable platform. A spacecraft tries to copy these functions, but in a tiny artificial way. A spacesuit copies them in an even smaller way. Every oxygen tank, pressure seal, cooling tube, carbon dioxide scrubber, water recycler, radiator, and emergency alarm is just technology trying to imitate what Earth does naturally. And Earth does it silently. That is why deep space is so terrifying. It does not have to be actively violent. It simply does not provide the conditions your body assumes will exist. Your lungs assume pressure. Your blood assumes pressure. Your cells assume liquid water. Your skin assumes a certain radiation level. Your brain assumes oxygen delivery. Your bones assume gravity. Your psychology assumes connection, day-night rhythm, open space, and safety. Deep space removes all of it. Imagine a fish suddenly pulled from water. The fish is not defective. It is simply outside the environment it was built for. That is the human body in deep space. We are not designed for vacuum. We are not designed for cosmic radiation. We are not designed for permanent weightlessness. We are not designed to live inside sealed machines forever. We can survive there only by carrying a small version of Earth with us. And if that artificial Earth fails, even for a few seconds, the universe reminds us what it really is. Not evil, not angry, just incompatible with human life. Part 4. The first killer. Pressure disappears. The first serious danger in space is not cold. It is not darkness. It is not even radiation. It is the sudden disappearance of pressure. On Earth, the atmosphere presses on your body all the time. At sea level, that pressure is about 14.7 pounds per square inch. You do not feel crushed because the pressure inside your body pushes back. Your fluids, tissues, blood, and lungs are all balanced with the outside environment. That balance is so normal that you never notice it. But your body depends on it. Your lungs work because of pressure differences. When you inhale, your diaphragm moves and your chest cavity expands. This lowers the pressure inside your lungs and outside air rushes in. When you exhale, your chest compresses, pressure rises inside the lungs and air moves out. Breathing is pressure mechanics. Your blood also depends on pressure. Your heart pumps blood through arteries and veins in a system designed for Earth conditions. Your cells exchange gases and fluids according to balances that assume a stable external pressure. Even the gases dissolved in your body are held there partly because of pressure. Now imagine that pressure vanishes almost instantly. Not slowly, not gently, instantly. That is what happens in vacuum exposure. The air outside your body is gone. The pressure holding gases in place is gone. The environment your body was calibrated for disappears. This does not mean your body explodes. That is the movie version. But it does mean your body begins swelling because gases inside tissues and fluids expand. The skin can stretch. The tissues can expand. The body can become visibly bloated. But the deeper danger is inside. Think of a soda bottle. While the bottle is sealed, carbon dioxide remains dissolved in the liquid because pressure keeps it there. Open the cap, pressure drops, and bubbles form. The gas escapes from solution. A similar principle applies inside the body. Your blood and tissues contain dissolved gases. Nitrogen, oxygen, carbon dioxide, all of them exist in balance under normal pressure. When pressure suddenly drops, gases can come out of solution and form bubbles. This is related to what divers call the bends, or decompression sickness. If a diver rises too quickly from deep water, pressure decreases too fast. Dissolved gases can form bubbles inside the body, causing pain, injury, and even death. But vacuum exposure is far more extreme. A diver may go from several atmospheres of pressure back to 1 atmosphere. A person exposed to space goes from 1 atmosphere to almost 0, and it happens immediately. That is why pressure loss is so terrifying. It attacks the body at a basic physical level. It does not wait for oxygen to run out slowly. It changes the behavior of fluids and gases inside you. The lungs face their own crisis. At normal pressure, the lungs contain air, but when outside pressure drops, that air expands. If a person holds their breath, the expanding air can damage or rupture delicate lung tissue. The lungs are not built to contain expanding gas against vacuum. They are soft biological organs, not metal tanks, so the instinct to hold breath becomes dangerous. The correct response would be to exhale, allowing expanding air to escape, but even that does not solve the larger problem. It may reduce lung injury, but the body is still exposed to vacuum. Blood gases are still unstable, oxygen supply is still gone, moisture is still vaporizing, consciousness is still fading. This is why a spacesuit must maintain pressure. Oxygen alone is not enough. You could surround a person with oxygen, but without pressure, the lungs cannot use it normally. The body needs oxygen at a usable partial pressure. It needs a pressurized environment so breathing, circulation, and fluid balance can continue. A spacesuit is not simply an oxygen mask. It is a pressure vessel shaped like a human. That is what makes it so difficult to design. The suit must hold pressure, but it must also bend. It must protect the astronaut, but still allow movement. It must be strong enough to resist vacuum, but flexible enough for hands, arms, legs, and tools. Every time an astronaut performs a spacewalk, they are inside a wearable pressure world. Outside that suit is vacuum. Inside is survival. The difference between the two may be only a few layers of material, seals, valves, and engineering. And if that pressure boundary fails, the countdown begins. Not a countdown of hours, a countdown of seconds. Part 5. Blood becomes a dangerous fluid. Blood is supposed to be the body's delivery system. It carries oxygen to the brain. It carries nutrients to tissues. It removes waste. It keeps organs alive. Every second of your life, blood is moving through a massive network of arteries, veins, and tiny capillaries. On Earth, this system works because the body exists in a stable pressure environment. In space vacuum, that stability breaks. When external pressure disappears, gases dissolved in the blood and tissues can begin coming out of solution. They form bubbles. And once bubbles form inside a circulatory system, the blood is no longer just a smooth liquid delivery network. It becomes unreliable. Imagine a city where every road must stay open. Ambulances, food trucks, water tankers, electricity repair crews, everything depends on roads. Now imagine bubbles, blockages, and broken sections appearing all over those roads at the same time. Deliveries slow down. Some areas receive nothing. Critical systems fail. That is what gas bubbles can do inside the body. Blood vessels are not designed to carry foam. Capillaries are extremely small. Some are so narrow that red blood cells must pass through one at a time. If gas bubbles interfere with that flow, tissues can be starved of oxygen even faster. The brain is especially vulnerable. Your brain is only a small part of your body weight, but it consumes a huge amount of oxygen. It has almost no patience for interruption. If oxygen delivery drops, consciousness fades quickly. The brain does not have minutes of comfortable backup. It has seconds of function before failure begins. This is why vacuum exposure can make a person lose consciousness in roughly 10 to 15 seconds. The blood still contains some oxygen at first, but the system delivering it is under attack. The lungs are no longer receiving normal air. Pressure has vanished. Gas bubbles may be forming. Circulation becomes compromised. The body is not dying from one cause. It is being overwhelmed by several failures at once. This is what makes deep space exposure different from simply holding your breath. If you hold your breath on Earth, pressure remains normal. Your blood continues circulating. Your lungs still contain air. Oxygen levels drop gradually. Carbon dioxide rises. You may panic, but the body's physical environment remains stable. In vacuum, the environment itself changes. The blood is not just running low on oxygen. It is experiencing a pressure crisis. The gases inside it are no longer behaving normally. The tissues surrounding blood vessels are swelling. The lungs are emptying or damaged. Exposed moisture is vaporizing. The whole system is collapsing. And because everything happens fast, there is very little time to respond. This is why documented vacuum accidents are so important. In controlled testing environments, some people have survived very brief exposure to near vacuum because they were repressurized quickly. These cases show that the human body does not instantly explode. They also show how narrow the survival window is. A few seconds can be survivable. Longer exposure becomes catastrophic. The difference between recovery and irreversible damage may be measured in moments. Think about how fragile that is. On Earth, if something goes wrong, you may have time. If you fall, someone can help. If you stop breathing, emergency responders may have minutes. If you are injured, medicine may save you. In space, some failures compress survival into seconds. Blood is the center of this problem because every organ depends on it. If blood flow becomes disrupted, the entire body suffers at once. The heart may keep beating for a short time, but what is it pumping? If the fluid is filled with bubbles, if pressure balance is broken, if oxygen is not entering properly, then the heartbeat alone cannot save the body. That is the horror. The body may still be trying to live while physics is making normal life impossible. The heart beats. The brain searches for oxygen. The lungs try to respond. The tissues swell. The blood becomes unstable. And outside, deep space remains perfectly silent. No violence, no sound, no mercy. Just vacuum doing what vacuum does. Part 6. Your saliva would boil, but not from heat. One of the most disturbing facts about deep space is this: your saliva can start boiling on your tongue, but not because space is hot, not because your mouth is burning, not because some invisible fire is touching you. It happens because pressure has disappeared. On Earth, we connect boiling with heat. You put water on a stove, the temperature rises. At sea level, water reaches 100 degrees Celsius or 212 degrees Celsius and it boils. That feels simple. Heat causes boiling, but that is only part of the story. Boiling is not just about temperature, it is also about pressure. Water boils when its vapor pressure becomes strong enough to overcome the pressure pushing down on it. At sea level, the atmosphere presses down hard enough that water needs a lot of heat before it can turn into vapor rapidly. But when pressure drops, water does not need as much heat to boil. This is why water boils at a lower temperature on high mountains. At the top of Mount Everest, the air pressure is much lower than at sea level. Because of that, water boils at a much lower temperature. You can heat water, see it boiling, and still find that it is not as hot as boiling water at sea level. Now take that idea to the extreme. In deep space, the pressure is almost zero. There is almost nothing pushing down on exposed liquid. So liquid water does not behave the way it behaves in your kitchen, your bathroom, your body, or anywhere on Earth's surface. At the temperature of the human body, exposed moisture can begin to vaporize rapidly. That means the moisture on your tongue, in your mouth, around your eyes, and inside your airway can start bubbling away. This sounds like horror fiction, but it is physics. The important detail is this: your entire body would not instantly become a boiling pot. Your skin and tissues provide some containment. Blood inside vessels does not simply erupt out of you like water from an open pan. The body has structure. The skin is a barrier. The tissues hold together for a short time. But exposed moisture is different. Your saliva is exposed. The wet surface of your eyes is exposed. The moisture inside your mouth and throat is exposed. And once pressure drops, that moisture becomes unstable. Imagine opening your mouth in a world where the liquid on your tongue suddenly realizes there is no atmosphere holding it down. It does not wait for fire. It does not wait for a stove. Your own body temperature is enough for it to begin escaping into vapor. This is why some vacuum exposure survivors described the sensation of saliva boiling before they lost consciousness. That detail is so chilling because it is not dramatic exaggeration. It is exactly the kind of strange, unnatural sensation a human body can experience when Earth's pressure vanishes. And this is where deep space becomes psychologically terrifying, because the danger is not just pain, it is confusion. Your body is experiencing something it has no instincts for. Humans understand heat. Humans understand cold. Humans understand drowning. Humans understand choking. But the feeling of your mouth moisture boiling from pressure loss is not something evolution prepared you to recognize. There is no ancient survival memory for vacuum. No instinct says, this is what space exposure feels like. There is only panic, physics, and seconds. The eyes would also suffer. Your tears and surface moisture help protect your eyes. In vacuum, that moisture would evaporate rapidly. Your eyes would not explode, but they would dry and become damaged. The surface would be exposed to both vacuum effects and intense radiation if unshielded. Inside the airway, moisture loss and bubbling would add to the chaos. The lungs and throat are supposed to stay wet. That wetness helps gases exchange, protects tissues, and keeps the respiratory system functioning. Vacuum turns that normal moisture into another vulnerability. And remember, all of this is happening while oxygen is already disappearing and blood gases are becoming unstable. That is why space exposure is not one simple death mechanism. It is not you run out of air. It is not you freeze. It is a full-body physics failure. Pressure disappears. Gases expand. Moisture vaporizes. Blood chemistry destabilizes. The lungs lose function. The brain loses oxygen. The body swells. And consciousness begins to fade. What makes this so powerful for the viewer is that it changes the way they imagine space. Space is not just emptiness. It is an environment where the basic rules your body relies on stop applying. The water in your body is not magic. It obeys pressure. The gases in your blood are not magic. They obey pressure. Your lungs are not magic. They obey pressure. Deep space does not break the laws of nature. It follows them perfectly. The problem is that those laws were never written for human comfort. Part 7. Why holding your breath could kill you faster. Now imagine the moment a person is suddenly exposed to vacuum. What is the first instinct? Hold your breath. It feels obvious. If you are underwater, you hold your breath. If smoke fills a room, you hold your breath. If dust or poison is in the air, you close your mouth and protect your lungs. The body's natural reaction is to keep the air inside. But in deep space, that instinct can become deadly, because the air inside your lungs is no longer safe. It is expanding. On Earth, air inside your lungs is balanced by the pressure outside your body. The pressure in your chest, the pressure in your airways, and the pressure in the surrounding atmosphere all work together. Your lungs are soft, delicate, flexible organs. They are not built like steel tanks. When outside pressure drops to near zero, the air already inside your lungs tries to expand. That is basic gas behavior. When pressure decreases, gas expands. If your mouth is open and you exhale, some of that expanding air can escape. That does not save you from vacuum exposure, but it may reduce the chance of lung rupture. But if you hold your breath, the expanding gas has nowhere to go. The lungs can overexpand. Tiny air sacs inside the lungs called alveoli can tear. Air can enter places where it should never go. Blood vessels can be damaged. Gas can be forced into the bloodstream. The injury can be devastating. This is why scuba divers are trained never to hold their breath while ascending. Even underwater, pressure changes matter. At depth, air is compressed. As a diver rises, pressure decreases and the air in the lungs expands. If the diver holds their breath, that expanding air can injure the lungs. Now take that same principle and make it extreme. Going from underwater to the surface is a pressure change. Going from Earth atmosphere to space vacuum is a pressure collapse. It is faster, harsher, and less forgiving. So the thing your body wants to do, hold air inside, can make the damage worse. That is one of the cruelest parts of space exposure. Your instincts are Earth instincts. They were built for forests, rivers, caves, storms, fire, predators, and drowning. They were not built for vacuum. In space, your body is facing a danger so alien that some of its automatic responses become useless or harmful. The correct action, if vacuum exposure were unavoidable, would be to exhale immediately. Let the air out. Do not trap expanding gas inside the lungs. But even that only buys a tiny amount of time, because the lungs are just one part of the problem. You still have no breathable atmosphere. You still have no pressure holding exposed moisture stable. You still have gases coming out of solution in the body. You still have oxygen delivery collapsing. You still have the brain consuming its last available oxygen. And you still have only seconds before consciousness fades. This is why the idea of surviving by holding your breath is one of the most dangerous space myths. It makes sense in normal life. It fails in vacuum. A person thrown into space would not be helped by taking a deep breath and sealing it in. That deep breath could increase the pressure inside the lungs relative to the outside vacuum. The lungs would be placed under dangerous stress at the exact moment the rest of the body is already failing. The better mental picture is not drowning. It is explosive decompression, not an explosion of the whole body, but a rapid pressure event where air, gases, and fluids suddenly try to adjust to an impossible environment. And the lungs are the first soft boundary between inside and outside. They are not designed to be that boundary. A spacesuit solves this by maintaining pressure around the body. The astronaut does not have to fight the vacuum directly. The suit provides a controlled environment so the lungs can keep working normally. The pressure does not have to equal sea level exactly, but it must be high enough for the body to function and for oxygen to be usable. Without that pressure, oxygen alone is not enough. A mask in vacuum would not save you if the rest of the body is exposed. You need pressure around the body. You need pressure for the lungs. You need pressure for fluids. You need pressure for circulation. That is why spacesuits are sealed pressure systems. That is why spacecraft cabins are pressurized. That is why a tiny leak becomes serious. Because once pressure drops, everything else begins to fail. The lungs are not just organs of breathing in space. They become a danger point. They are filled with gas, and gas expands when pressure falls. So in the first seconds of vacuum exposure, the human body is caught in a terrible contradiction. It needs air, but trapped air can injure it. It needs pressure, but pressure is gone. It needs oxygen, but oxygen cannot be delivered normally, and the one instinct that feels most human, holding your breath, can become the wrong move. That is why deep space is not just hostile, it is alien to the body's survival logic. Part 8. The 15-second consciousness window. If a person were suddenly exposed to the vacuum of space, the most terrifying part is how little time they would have. Not minutes, not a long struggle, not enough time to think clearly through a plan. The conscious window may be only around 10 to 15 seconds. That is shorter than most people take to unlock a phone, shorter than walking across a room, shorter than finishing one full sentence slowly. And in those few seconds, the body is already entering crisis. At 0 seconds, pressure disappears. The environment around the body drops from Earth-like pressure to near vacuum. The outside world no longer supports breathing, fluid stability, or normal gas behavior. If this happens suddenly, the body has no time to adjust. At 1 second, air begins rushing out. If the person does not hold their breath, air leaves the lungs rapidly. If they do hold their breath, expanding gas can injure the lungs. Either way, normal breathing is over. There is no usable air outside the body. The lungs are no longer operating in an atmosphere. At 2 to 3 seconds, exposed moisture starts to change. Saliva on the tongue may begin to bubble. Moisture in the mouth, nose, and throat can vaporize. The wet surface of the eyes starts losing moisture quickly. This is not because the body is heating up. It is because the pressure is too low for exposed liquid to remain stable. At 5 seconds, swelling becomes more noticeable. Gases inside tissues expand. The skin stretches. The body may begin to look bloated. This is not an explosion, but it is a serious physical response. The body is being pulled away from the pressure conditions it was designed to survive. At 8 seconds, oxygen delivery to the brain is falling fast. The brain is an oxygen-hungry organ. It consumes a large share of the body's oxygen supply even though it is only a small part of body weight. It has almost no ability to pause. It does not wait patiently for conditions to improve. When oxygen delivery drops, consciousness begins to fail. At 10 seconds, vision may narrow. The edges of sight can darken. The person may feel disoriented. Hearing may fade. Thought becomes harder. Panic may be present, but even panic requires a working brain. The ability to make decisions is already being compromised. At 12 to 15 seconds, consciousness may be lost. This is the point where the person is no longer experiencing the event in a normal conscious way. The body is still there, the heart may still be beating, but awareness is gone. That is the brutal timeline. The most terrifying suffering may be brief because the brain shuts down quickly. But the body's crisis continues. After 20 to 30 seconds, circulation is badly compromised. Gas bubbles, swelling, and oxygen loss are all interfering with normal function. The heart may still try to pump, but the blood is no longer part of a stable system. Around 1 minute, the risk of severe brain injury grows. Brain cells cannot survive long without oxygen. Some damage may still be reversible if repressurization happens quickly enough, but the margin is narrowing fast. After 90 seconds to 2 minutes, survival becomes extremely unlikely without immediate rescue and medical support. The heart may fail. Brain activity may collapse. The body has been outside its survivable environment too long. This is why short exposure cases matter so much. They show that vacuum exposure is not instant death in the first second, but they also show that the survival window is terrifyingly small. A person might survive a very brief near-vacuum accident if repressurized quickly, but that is in a controlled chamber, with people nearby, with emergency systems ready. Deep space is different. There may be no one close enough, no chamber, No fast repressurization, no rescue team standing outside the door. If the suit fails far from an airlock, seconds decide everything. This timeline also destroys another movie myth, the idea that someone could drift in space, remain conscious, speak emotionally, and wait for rescue while exposed. No. Without pressure and oxygen, the brain does not allow that. Consciousness is expensive. It requires oxygen, blood flow, and stable chemistry. Vacuum strips those away quickly. And the body is not waiting for one system to fail. Multiple systems fail together. Lungs lose function, blood flow becomes unstable, moisture vaporizes, tissues swell, the brain starves, the heart struggles, the skin stretches, the eyes dry. The person loses awareness. Deep space compresses disaster. It turns what sounds like a survival situation into a countdown measured in breaths the person can no longer take. That is why astronauts do not simply trust courage. They trust seals. They trust pressure gauges. They trust oxygen systems. They trust cooling loops. They trust alarms. They trust checklists. Because in space, bravery does not stop vacuum. Only working engineering does. Part 9. Space is not just cold, it is thermally strange. Everyone says space is cold, and they are not exactly wrong. But they are also not understanding the full picture. Space is not cold like a winter night. It is not cold like ice water. It is not cold like standing in freezing wind. Space is thermally strange because space has almost no matter. Temperature, in the normal everyday sense, is about the motion of particles. Air feels warm or cold because air molecules are hitting your skin and transferring energy. Water feels cold because water molecules are pulling heat from your body. Metal feels cold because it conducts heat away from your hand quickly. But in deep space, there are almost no particles touching you. There is no air. No wind, no water, no surface. So heat does not leave the body the way it does on Earth. On Earth, your body loses heat in 3 main ways: conduction, convection, and radiation. Conduction is direct contact. Touch cold metal, and heat flows from your hand into the metal. Convection is moving fluid or air carrying heat away. Cold wind feels worse than still air because moving air keeps removing warmth from your skin. Radiation is heat leaving as infrared energy. Your body constantly emits infrared radiation because it is warm. In space, conduction and convection are nearly gone. There is almost nothing to touch you and almost nothing to flow past you, so the main way you lose heat is radiation. That process is real, but it is slower than people imagine. This is why a person exposed to space would not instantly freeze solid. They would lose consciousness from pressure loss and oxygen deprivation long before their body froze. The movie image of someone turning into a frozen statue in seconds is visually powerful, but scientifically misleading. The immediate killer is not freezing. It is vacuum, but temperature in space is still dangerous. It is just dangerous in a different way. If you are far from any star, surrounded by deep interstellar darkness, there is very little external heat. Over time, an object will radiate away its heat and cool dramatically. A body in that environment would eventually freeze, but not instantly. Near a star, the problem becomes more complicated. Take the sun. Near Earth's orbit, sunlight is intense. Without an atmosphere, there is nothing to soften it. No clouds, no scattering, no air to distribute heat. If one side of an object faces the sun and the other side faces darkness, the temperature difference can become extreme. One side heats, the other side cools. On Earth, air helps move heat around. If sunlight warms one side of your body, surrounding air carries some heat away. Your blood circulation also distributes warmth internally. But in space, the outside environment does not help. The sunlit surface receives direct radiation. The shaded side radiates heat into darkness. That is why spacecraft need thermal control systems. They are not simply trying to stay warm. Often, they are trying to get rid of heat. Electronics generate heat. Humans generate heat. Life support systems generate heat. Computers, pumps, batteries, radios, lights, and instruments all create heat. In vacuum, that heat cannot be removed by opening a window or running a fan into outside air. There is no outside air. Heat must be moved to radiators and released as infrared radiation into space. This is why spacecraft often have radiator panels. They are like the sweat system of the spacecraft, except they do not sweat. They radiate heat away. A spacesuit has the same problem on a smaller scale. The astronaut's body generates heat. Working in a pressurized suit is physically difficult. The astronaut may be producing far more heat than at rest, but the suit is sealed. That heat must be removed, usually by a liquid cooling garment that circulates water close to the body. Without cooling, the astronaut can overheat. That surprises people. They imagine space as freezing, but an astronaut inside a suit can become dangerously hot because their own body heat has nowhere easy to go. So space gives both dangers. Too much cold over time, too much heat when systems fail, sunlight burning one side, shadow freezing the other, no air to balance anything, no environment to soften extremes. This is why space is not just cold, it is uncontrolled. On Earth, temperature is moderated by atmosphere, oceans, winds, humidity, clouds, and ground. In space, those buffers are gone. Every object becomes responsible for its own heat balance. A spacecraft must manage heat like it manages oxygen and pressure. If it fails, electronics can shut down, batteries can overheat, fluids can freeze, seals can crack, and the crew can become unsafe. Deep space does not simply freeze humans. It removes the entire thermal safety system Earth provides. And once again, survival depends on machines, not strength, not courage, not luck. Machines. Part 10. The Invisible Bullets, Radiation. If vacuum is the fast killer, radiation is the patient one. It may not knock you unconscious in 10 seconds. It may not make your saliva boil. It may not tear your lungs immediately. But it is always there, silent, invisible, passing through space, through metal, through skin, through cells, and sometimes through DNA. On Earth, we are protected from much of this danger without thinking about it. The atmosphere blocks and absorbs many harmful forms of radiation. The magnetic field deflects charged particles from the sun and from deep space. The ozone layer filters dangerous ultraviolet radiation, but in deep space, that protection is gone. There is no thick atmosphere above you, no ozone layer, no strong planetary magnetic shield, just your spacecraft, your suit, or whatever shielding engineers could afford to launch. Radiation in space comes in several forms. The first is solar radiation. The sun gives us visible light, warmth, and life. But it also produces ultraviolet radiation, X-rays, and high-energy particles. On Earth, the atmosphere filters much of the worst of it. In space, the sun is raw, unfiltered, direct. Ultraviolet radiation can damage skin and eyes. It can break molecular bonds and harm DNA. On Earth, a bad sunburn is already a sign of radiation injury. In space, without protection, ultraviolet exposure would be far more intense. But ultraviolet radiation is only the beginning. The more serious long-term danger comes from ionizing radiation. Ionizing radiation has enough energy to knock electrons off atoms. That may sound small, but inside living tissue, it can create chemical chaos. It can damage DNA. It can break molecules. It can kill cells or mutate them. Some mutations are repaired. Some cells die. Some damaged cells survive in a dangerous form. That is where cancer risk comes in. Then there are galactic cosmic rays. These are among the most frightening particles in space. They are not rays in the ordinary sense. Many are atomic nuclei, mostly protons but also helium nuclei and heavier elements, moving at extremely high speeds. Some are accelerated by violent cosmic events like supernova explosions. Imagine an atomic bullet traveling close to the speed of light. That is not poetry. That is close to what a high-energy cosmic ray is. When one of these particles hits human tissue, it can slice through cells at the microscopic level. It can leave a trail of ionization behind it. It can damage DNA directly. It can also create secondary particles, causing damage beyond the original path. And the worst part is that shielding against cosmic rays is difficult. You might think thicker metal solves the problem, but not always. When high-energy particles hit metal, they can produce showers of secondary radiation. That means a shield can sometimes turn one dangerous particle into several damaging particles. Materials rich in hydrogen, like water or certain plastics, can be better for some shielding purposes, but effective protection requires mass. A lot of mass. And mass is the enemy of spaceflight. Every kilogram launched into space costs fuel. Every extra layer of shielding makes the spacecraft heavier. Heavier spacecraft require more powerful rockets, more fuel, more money, and more complexity. So engineers face an ugly trade-off. More shielding means better protection but harder missions. Less shielding means lighter spacecraft but higher radiation risk. Astronauts in low Earth orbit already receive much more radiation than people on the ground. They are still partly protected by Earth's magnetic field, but the dose is higher. On longer missions beyond Earth's protection, the exposure becomes more serious. A mission to Mars would take months each way. During that journey, astronauts would live outside Earth's magnetic shield. Every day, radiation dose would accumulate. It might not make them sick immediately, but it could increase lifetime cancer risk. It could affect the eyes. It could affect the cardiovascular system. There are also concerns about possible effects on the brain and nervous system during long missions. That is the scary part. Radiation is not always dramatic. It is cumulative. It builds. One particle does not necessarily destroy you, but millions of particles over months and years increase risk. And then there are solar particle events. Sometimes the sun releases massive bursts of charged particles during solar storms. If astronauts are caught unprotected, the dose can become dangerous quickly. A spacecraft traveling to Mars would need a radiation shelter, a small area with extra shielding where the crew could hide during a major event. Imagine that. You are millions of miles from Earth. A warning comes in. Solar particle storm incoming. You cannot land. You cannot return home. You cannot run away from the sun. You can only crawl into the most shielded part of your spacecraft and wait while invisible particles slam into everything around you. That is deep space. The danger is not always something you can see. Sometimes the thing trying to damage you is smaller than an atom and older than human civilization. Radiation reminds us that space is not empty. It is filled with energy, filled with particles, filled with invisible violence, and without Earth's protection, the human body is exposed to a kind of threat it can neither sense nor stop. That is why radiation may be the greatest long-term barrier to human deep space travel. Vacuum kills quickly, radiation waits. But if humans want to live beyond Earth, they must solve both. Part 11. The sun can become a weapon. Most people look at the sun and think of warmth, light, morning, life. And on Earth, that is mostly true. The sun grows our food, it warms the oceans, it drives weather, it gives us daylight. Every plant, every animal, every human life is connected to the energy pouring from that star. But outside Earth's protection, the sun becomes something else. A radiation source, a storm engine, a weapon made of plasma, magnetism, and charged particles. On Earth, we are protected from the sun's worst behavior. Our atmosphere absorbs dangerous radiation. Our magnetic field deflects many charged particles. Even when the sun erupts violently, most people on the ground notice nothing more than news headlines, radio disruptions, or maybe beautiful auroras near the poles. But in deep space, there is no atmospheric shield. There is no planet-sized magnetic umbrella. There is only the spacecraft. And if the spacecraft is not prepared, one solar storm can turn a mission into a survival emergency. The sun is not calm. It only looks calm from far away. Its surface is constantly boiling with magnetic activity. Gigantic loops of plasma rise and twist. Magnetic fields tangle, snap, and reconnect. When this happens, the sun can release enormous bursts of energy called solar flares. Sometimes it also launches huge clouds of charged particles into space. These are called coronal mass ejections. To someone on Earth, that sounds like distant astronomy. To astronauts beyond Earth's magnetic field, it can become personal. Imagine a crew halfway to Mars. They are not in orbit around Earth anymore. They are not protected by the strongest part of Earth's magnetic field. They are living inside a metal shell moving through interplanetary space. The spacecraft is functioning. The crew is eating, sleeping, exercising, checking systems, trying to keep life normal. Then a warning arrives. Solar activity has increased. A flare has erupted. A storm of particles may be heading toward them. Suddenly, the mission changes. The crew must stop what they are doing. They move into the most shielded part of the spacecraft. Maybe that area is surrounded by water tanks, food supplies, equipment boxes, or specially designed radiation shielding. It may be cramped. It may be uncomfortable. But during a solar particle event, that small shelter becomes the safest place in the ship. They wait. Outside, there is no visible fire, no explosion hitting the windows, no monster approaching. But invisible charged particles are racing through space. That is what makes solar storms so frightening. You cannot see the danger with your eyes. You cannot hear it. You cannot feel the first particles hitting the spacecraft. But instruments can detect it, and biology can suffer from it. A strong solar particle event can deliver a dangerous radiation dose, especially to unprotected astronauts. It can damage cells, increase cancer risk, and in extreme cases, cause acute radiation sickness. The danger depends on the strength of the event, the shielding available, and how long the crew is exposed. This is one reason mission planners take space weather seriously. A journey to Mars is not just about rockets and fuel, it is also about timing, shielding, monitoring, and emergency procedures. The crew must know where to go if the sun becomes active. The spacecraft must have enough protection to reduce the dose. Mission control must watch solar activity constantly. The scary part is that solar storms are not perfectly predictable. We can monitor the sun, we can detect eruptions, we can estimate when particles might arrive. But the sun is a complex star, and space weather can change quickly. During the Apollo missions, astronauts traveled beyond Earth's safest radiation protection. They were lucky that no major solar particle event hit during their lunar journeys. If a severe event had occurred at the wrong time, the outcome could have been very different. That is not meant to take away from their courage or achievement. It makes the achievement even more intense. Those missions were not casual adventures. They were humans crossing a dangerous environment with limited protection, limited computing power, and no guarantee that the sun would remain quiet. Future missions will have better monitoring, better spacecraft, better procedures, but the sun will still be the sun. It will still flare. It will still throw particles into space. It will still remind humans that the star giving Earth life can also become deadly when faced without Earth's protection. And this is the strange truth of space exploration. The same sun that makes life possible on our planet becomes one of the major threats once we leave it. On Earth, sunlight feels like safety. In deep space, sunlight must be measured, filtered, shielded, and feared. Because beyond our atmosphere, the sun is not just a light in the sky. It is a nuclear furnace with moods. And when it erupts, astronauts do not argue with it. They hide. Part 12. Spacesuits are not clothing, they are tiny spacecraft. A spacesuit looks simple from far away. White fabric, helmet, gloves, boots, backpack. To most people, it looks like a special uniform. But that is completely wrong. A spacesuit is not clothing. A spacesuit is a personal spacecraft shaped around a human body. It must do almost everything a spacecraft does, but in a smaller, wearable form. It must provide pressure, oxygen, cooling, communication, radiation protection, micrometeoroid protection, carbon dioxide removal, and enough mobility for the astronaut to work. That is a ridiculous engineering challenge. Because the suit must keep a human alive in an environment where the human body should fail within seconds. Start with pressure. Without pressure, the astronaut cannot survive. So the suit must hold an internal atmosphere around the body. It does not always use the same pressure as Earth at sea level. Many spacesuits use lower pressure, often with a higher oxygen concentration, because a lower pressure suit is easier to move in. But lower pressure creates its own challenges. The body still needs enough oxygen partial pressure to breathe properly. Oxygen must be delivered at the right amount. Carbon dioxide must be removed continuously. If oxygen drops too low, the astronaut can become confused, weak, unconscious. If carbon dioxide rises too high, the astronaut can develop headaches, dizziness, panic, and eventually lose consciousness. So the suit must not only provide air, it must manage air chemistry. Every breath becomes part of a machine cycle. The astronaut inhales oxygen. The astronaut exhales carbon dioxide. The suit removes that carbon dioxide. Fresh oxygen is supplied. Pressure is maintained. The cycle continues. If that cycle stops, the astronaut is in danger. Then comes temperature control. This is one of the parts people do not expect. Space is known as cold, but astronauts inside suits can overheat. The human body produces heat, especially when working hard. A spacewalk is physically exhausting. The astronaut is pushing against a pressurized suit, using tools, moving slowly, concentrating for hours. That body heat has nowhere easy to go. There is no air outside to carry it away. So astronauts wear a liquid cooling garment under the suit. It is like a layer of clothing with tubes running through it. Cool water circulates through those tubes and pulls heat away from the body. That heat is moved to the suit's backpack system and eventually released. If cooling fails, the astronaut can overheat dangerously. So once again, survival depends on pumps, tubes, sensors, and heat exchangers. Then there is movement. A pressurized suit naturally wants to become stiff. Pressure pushes outward in every direction. The suit wants to inflate, almost like a balloon. But astronauts need to bend their arms, move their fingers, turn their heads, grip tools, attach cables, repair equipment, and climb around outside spacecraft. That means the suit needs joints, shoulders, elbows, wrists, knees, ankles, gloves, each must move while still holding pressure. This is harder than it sounds. Every movement fights the suit. Bending a pressurized glove is like squeezing against resistance again and again. After hours, hands become tired, fingers hurt. Some astronauts have experienced fingernail injuries from working inside stiff gloves. That detail matters because it shows the reality of spacewalks. They look slow and peaceful on camera. But inside the suit, the astronaut may be sweating, breathing hard, fighting stiffness, checking oxygen, watching time limits, managing tools, and trusting that every seal remains intact. The helmet is also more than a window. It protects the face and eyes. It must resist impact from tiny particles. It must handle sunlight. It must prevent fogging. It must allow communication. It must keep pressure sealed around the head while giving the astronaut enough visibility to work. The backpack is life support. It contains oxygen systems, carbon dioxide removal, cooling systems, power, communication equipment, fans, pumps, sensors, and emergency reserves. It is the difference between a human in space and a body exposed to vacuum. This is why a spacesuit costs so much and takes so long to design. It is not a costume, it is a life support machine, and it has to work while being bent, bumped, heated by sunlight, cooled by shadow, exposed to vacuum, hit by radiation, and operated by a human who may be tired, stressed, and millions of dollars away from safety. The suit is also limited. It cannot support someone forever. Oxygen runs down. Carbon dioxide removal has a limit. Battery power has a limit. Cooling systems have a limit. Spacewalks are planned around these limits, usually lasting several hours, with safety margins included. The astronaut is not free outside the spacecraft. They are on a countdown. Every minute outside uses resources. Every task must be planned. Every delay matters. And this is what makes a spacesuit so fascinating and terrifying at the same time. It gives humans the power to step into an environment where humans do not belong, but it also reminds us how completely we depend on technology there. One suit, one pressure seal, one cooling loop, one oxygen system, one small artificial world. That is all standing between the astronaut and deep space. Part 13. The suit can save you, but it can also fail. A spacesuit is one of the most impressive machines ever built. But it is still a machine, and machines can fail. That is what makes every spacewalk dangerous. Not because astronauts are careless, not because engineers are unskilled, but because space leaves almost no margin for error. On Earth, if a glove tears, it is annoying. In space, glove damage can become a serious warning. On Earth, if your cooling system fails, you step outside, open a window, drink water, or stop working. In space, if the cooling system fails, body heat builds inside a sealed suit. On Earth, if water leaks into your helmet, you remove the helmet. In space, removing the helmet is impossible. That is the horror of suit failure. The thing protecting you can become the thing trapping you. A spacesuit must remain sealed, pressurized, cooled, powered, and chemically balanced. If one system starts failing, the astronaut may have only minutes to return to the spacecraft. Consider a cooling problem. Inside the suit, the astronaut's body is constantly producing heat. During hard work, that heat rises. The suit must remove it. If cooling water stops flowing or a pump fails, heat begins accumulating. The astronaut may feel warm first, then uncomfortable, then dangerously overheated. Sweating does not solve the problem the way it does on Earth. Sweat cools you when it evaporates into air. But inside a sealed suit, moisture and humidity must be controlled by the suit system. If the system cannot manage heat and moisture, the astronaut's body temperature can rise. Heat stress can cause confusion. Confusion during a spacewalk is dangerous. A confused astronaut may make slow decisions, miss a safety step, drop a tool, lose orientation, or fail to return quickly enough. Now consider carbon dioxide. The astronaut breathes oxygen and exhales carbon dioxide. If the suit's CO2 removal system is not working properly, carbon dioxide levels rise. At first, there may be headache or discomfort, then dizziness, then panic, then mental confusion. Eventually, unconsciousness. This is frightening because the astronaut may still have oxygen, but the air becomes toxic because waste gas is not being removed. Breathing is not enough. The suit must keep the air chemically safe. Then there is water. Water inside a helmet is one of the most terrifying suit problems because in weightlessness, water does not fall downward. It floats, it clings, it forms blobs. It can move across the face, cover the eyes, enter the nose, and block breathing. Imagine being in a sealed helmet where water begins floating around your face. You cannot wipe it away normally. You cannot take the helmet off. You may not be able to see clearly. Your communication may become urgent, and you still have to move carefully back to the airlock. That kind of failure shows how alien space is. On Earth, water leaks downward because gravity pulls it. In orbit, water behaves differently. A small leak can become a moving hazard inside the helmet. Even a tiny suit leak matters. A small pressure leak may not kill instantly, but it starts a countdown. The suit must maintain pressure. If it loses pressure faster than it can compensate, the astronaut must return immediately. The leak could worsen. Oxygen supply could drain. Pressure could fall below safe limits. And outside the suit is vacuum. There is no backup atmosphere around the astronaut. Only the spacecraft or airlock can provide safety. This is why astronauts train so intensely. They rehearse emergencies. They practice abort procedures. They learn how to move back to the airlock if something goes wrong. They learn to communicate clearly, conserve oxygen, handle tools, and avoid panic. But training does not remove danger. It only helps humans respond before danger becomes fatal. The suit also faces external threats. Tiny particles can strike it. Sharp edges on equipment can damage gloves or outer layers. Extreme sunlight can heat surfaces. Shadow can cool them. Radiation passes through more than people imagine. The astronaut is moving in a place where normal repair rules do not apply. If a component fails, there is no workshop outside, no chair to sit on. No fresh air, no safe ground, only a rail, a tether, and the airlock somewhere nearby. This is why spacewalks are planned like surgical operations. Every movement is choreographed. Every tool is tethered. Every task has a time estimate. Every risk is reviewed. Every emergency has a procedure. The calm videos we see from space do not show the pressure behind the scenes. They do not show the hours of planning. They do not show the fear of one small malfunction. They do not show how many people are watching every sensor reading, every oxygen number, every pressure value, every cooling signal. A spacesuit can make a human look powerful, but the truth is more fragile. The astronaut is alive because a machine is winning a battle against space every second. And if that machine begins losing, deep space is waiting immediately outside. No delay, no mercy, no second atmosphere, just vacuum. Part 14, spacecraft are fragile islands in a vacuum ocean. From the outside, a spacecraft can look strong. Metal body, solar panels, hatches, modules, engines. It looks like a machine built to conquer space. But the truth is more delicate. A spacecraft is not a fortress. It is a fragile island of pressure, warmth, oxygen, and order floating inside a vacuum ocean. Inside, humans can breathe. They can sleep. They can eat. They can talk. They can look out the window and see Earth, Mars, or stars. Outside, there is nothing their bodies can survive. The difference between those two realities may be a wall only a few millimeters thick. That sounds impossible, but spaceflight is controlled by mass. Every kilogram matters. A thicker hull means more weight. More weight means more fuel. More fuel means a bigger rocket. A bigger rocket means more cost, more complexity, and more failure points. The rocket equation is merciless. You cannot build a spacecraft like a bunker and easily launch it. Engineers must make it light enough to reach orbit or deep space, but strong enough to hold pressure and survive mission hazards. So spacecraft walls are carefully designed, but they are not infinitely thick. They are thin because they have to be, and that thin wall becomes the boundary between life and death. One serious puncture can turn the cabin into an emergency. If a micrometeoroid hits the spacecraft, it may be tiny, maybe smaller than a grain of sand, but speed changes everything. Objects in space can travel at kilometers per second. At those speeds, even small particles carry destructive energy. A tiny object moving fast enough can punch, crack, pit, or damage spacecraft surfaces. Space debris is another threat. Humanity has filled near-Earth space with old satellite fragments, rocket parts, paint flakes, bolts, and debris from collisions. Many of these pieces move at orbital velocities. A small fragment can behave like a bullet. This is the frightening part. In space, size is not the only danger. Velocity is danger. A paint fleck moving fast enough can damage a window. A small metal fragment can puncture equipment. A larger object can destroy a spacecraft. The International Space Station and other spacecraft use shielding to reduce this risk. One common concept is layered shielding. Instead of relying on one thick wall, engineers place layers with gaps between them. A small particle hits the outer layer, breaks apart, spreads out, and loses some of its destructive force before reaching the inner wall. This can work well against smaller debris, but it cannot stop everything. Something too large or too fast can still penetrate. That is why debris tracking is so important. Larger objects can be monitored. If a dangerous piece of debris is predicted to come close, spacecraft may maneuver away, but not every object can be tracked. Many pieces are too small to see reliably and still large enough to cause harm, so crews live with a strange reality. The probability of a catastrophic impact may be low, but it is never zero. And in space, low probability does not mean emotionally comfortable. It means every day depends partly on luck, engineering, and constant monitoring. A hull breach can happen in different ways. A tiny leak may cause pressure to drop slowly. The crew might hear a hiss, see pressure readings change, search for the leak, and patch it. That is frightening but manageable if found quickly. A larger breach is more dangerous. Air rushes out, pressure drops, alarms sound. The crew must isolate the affected compartment, seal hatches, use emergency masks or suits, and stop the leak if possible. If pressure falls too quickly, there may not be enough time. This is why spacecraft are divided into compartments. If one section is damaged, hatches can close to preserve the rest of the vehicle. But this only works if the damage is not too widespread and if the crew can respond in time. The spacecraft also has other fragile systems: power, thermal control, oxygen generation, carbon dioxide removal, water recycling, computers, communication, navigation, propulsion. A spacecraft is not just a metal shell, it is an ecosystem of machines. If one system fails, others may be affected. If cooling fails, electronics overheat. If power fails, fans stop. If fans stop, air may not circulate properly. If carbon dioxide removal fails, breathable air becomes dangerous. Everything is connected. That is why space missions are planned with redundancy. Critical systems often have backups. Sometimes backups have backups, but redundancy adds mass and complexity, and no system can be made perfectly safe. The spacecraft is always a compromise, strong but light, protected but launchable, complex but reliable, self-sufficient but repairable, comfortable enough for humans but efficient enough for mission limits. This is why deep space missions are so difficult. In low Earth orbit, emergency return may be possible, resupply may arrive, mission control can help in real time. But on a Mars mission, a spacecraft failure happens months from home. No repair crew is coming, no replacement spacecraft is nearby. The crew must fix the problem with what they have. That is why a spacecraft is best understood as a tiny island. Inside is Earth-like order, outside is cosmic indifference, and between them is engineering, not magic, not safety guaranteed, engineering. Part 15. Life support, the hidden system keeping astronauts alive. Inside a spacecraft, breathing feels simple. An astronaut inhales. An astronaut exhales. The cabin seems calm. Lights glow. Computers hum. Air moves through vents. The crew floats from one module to another as if living inside a small, futuristic home. But that calm is artificial. Every breath inside a spacecraft is produced, cleaned, measured, and protected by machines. On Earth, the planet handles life support for us. Plants, oceans, atmosphere, microbes, weather systems, pressure, gravity, all of it works together. We breathe without thinking because we live inside a natural system that has been stabilizing itself for billions of years. In space, that system must be built, and if it fails, the cabin stops being a home. It becomes a sealed container with humans consuming oxygen and producing waste. The first job of life support is oxygen. Humans need oxygen continuously. On a spacecraft, oxygen can come from stored tanks, chemical oxygen generators, or systems that split water into hydrogen and oxygen through electrolysis. The oxygen is released into the cabin so the crew can breathe. But adding oxygen is only half the problem. The crew also exhales carbon dioxide. On Earth, carbon dioxide disperses into the atmosphere and is absorbed by plants, oceans, and natural cycles. In a spacecraft, carbon dioxide builds up in a closed volume. If it is not removed, it becomes dangerous. At low levels, too much CO2 can cause headaches and tiredness. At higher levels, it causes dizziness, confusion, shortness of breath, panic, and eventually unconsciousness. So, life support systems must scrub carbon dioxide from the air constantly. Different systems can do this using chemical absorbers or regenerable filters. The goal is simple: keep the air breathable. But the process is not simple. Fans must move air. Sensors must measure gas levels. Filters must work, valves must open and close, power must stay on. If airflow stops in microgravity, carbon dioxide can collect around a person's head because warm, exhaled air does not rise normally the way it does on Earth. That means even air circulation matters. In space, a fan can be a survival device. Then comes humidity. Humans exhale moisture. They sweat. Water vapor enters the cabin air. If humidity gets too high, condensation forms on surfaces, electronics, walls, and equipment. Moisture inside spacecraft can be dangerous because it can damage systems, encourage microbial growth, and make the cabin uncomfortable. So humidity must be controlled. Water must be collected. Air must be dried and filtered. That collected water can then be purified and reused. Water recycling is one of the most important parts of long-duration spaceflight. Water is heavy. Launching large amounts of it from Earth is expensive and inefficient, so spacecraft recycle water from urine, sweat, breath moisture, and condensation. This sounds unpleasant at first, but purified recycled water can be extremely clean. The problem is not whether it can be cleaned. The problem is whether the system can keep working for months or years. Filters clog, pumps fail, sensors drift, valves stick, microbes grow, parts wear out. On the International Space Station, replacement parts can be sent from Earth. On a Mars mission, that luxury is limited. The crew must carry spare parts or repair systems themselves. Life support is not just technology, it is maintenance. Every day, the crew depends on machines that must keep doing boring jobs perfectly. Move air, clean air, remove CO2, control humidity, recycle water, manage waste, regulate temperature, detect fire, maintain pressure. None of these tasks are glamorous, but all of them are survival. Temperature control is another hidden battle. Inside the spacecraft, electronics generate heat. Human bodies generate heat. Batteries, computers, lights, pumps, and experiments all add warmth. In vacuum, that heat cannot simply drift away into air. It must be collected and moved to radiators, where it can be released into space as infrared radiation. If cooling systems fail, the spacecraft can overheat. If heating fails in the wrong area, fluids can freeze. Thermal balance must be managed constantly. Then there is fire. Fire in space is terrifying because the cabin is sealed. Smoke does not rise normally in microgravity. Flames behave differently. Toxic gases can spread through life support systems. The crew cannot simply run outside, so spacecraft must use fire-resistant materials, detectors, extinguishers, emergency masks, and strict rules about electrical systems. A small fire can become a mission-threatening event. Waste is another challenge. On Earth, waste disappears into large external systems: plumbing, landfills, recycling, soil, oceans, bacteria. In space, nothing disappears. Everything stays inside the mission unless it is stored, processed, recycled, or discarded in a controlled way. Food packaging, used filters, broken parts, human waste, medical waste, all of it must be managed. For short missions, storage is possible. For long missions, waste becomes a serious design problem. A spacecraft is a closed world, and closed worlds punish carelessness. This is why life support may be the most important invisible technology in space exploration. Rockets get the attention, engines get the drama, landings get the applause. But life support keeps the crew alive after the launch is over. It is the quiet system that turns a metal vehicle into a survivable habitat. And it must work every hour, every day, every night, for the entire mission. Because in space, breathing is not natural. Breathing is engineered. Part 16. The Mars Problem. Deep space for months. A journey to Mars does not begin with footprints on red dust. It begins with months of isolation inside a moving metal habitat, surrounded by vacuum, radiation, silence, and distance. That is the part most people skip. They imagine the launch. They imagine the landing. They imagine astronauts stepping onto Mars with flags, cameras, and heroic music. But between Earth and Mars is the real test: deep space. For 6 to 9 months, the crew would not be on a planet. They would not be in low Earth orbit. They would not be close to a space station. They would be inside a spacecraft traveling through interplanetary emptiness, far beyond the easy protection of Earth. And during that time, every normal human need becomes a technical problem. Air must be made or stored. Water must be recycled. Food must last. Waste must be managed. Radiation must be reduced. Heat must be controlled. Machines must keep running. People must stay sane. And if something breaks, help is not coming. Imagine this scenario. The spacecraft is 120 million miles from Earth. The crew is halfway to Mars. They are not close enough to turn around quickly, and they are not close enough to arrive soon. They are in the worst possible place, committed. Then a pump begins failing. At first, it is just a small warning. A temperature reading rises slightly. A pressure value looks wrong. A fan changes sound. The crew checks the data. Mission Control receives the same information, but delayed by distance. The signal takes minutes to reach Earth. Mission Control studies the problem, sends instructions back, and those instructions take more minutes to return. By the time Earth replies, the crew has already had to make decisions. That is the Mars problem. Distance changes everything. In low Earth orbit, astronauts can speak to Mission Control almost instantly. If something goes wrong, teams on Earth can help in real time. A return to Earth may be possible within hours. Supplies can arrive on cargo vehicles. Spare parts can be launched. Medical advice is immediate. Mars is different. Communication is delayed. Rescue is impossible. Resupply is not quick. The spacecraft must be its own hospital, workshop, shelter, laboratory, kitchen, water plant, oxygen plant, power station, and emergency bunker. This is why Mars missions are not just longer versions of space station missions. They are a different category of danger. On the way to Mars, the crew is outside Earth's strongest magnetic protection. Radiation exposure accumulates every day. Galactic cosmic rays pass through the spacecraft. Solar storms are a constant threat. The crew may have a storm shelter, but they cannot avoid all radiation. They can only reduce it. Then there is zero gravity. During months in weightlessness, muscles weaken, bones lose density, fluids shift toward the head. Vision can change. The heart and blood vessels adapt to an environment where they no longer need to fight gravity in the same way. Astronauts exercise for hours every day to slow these effects, but exercise does not completely erase them. Now imagine landing on Mars after months of this. The crew is weaker than when they left Earth. Their bodies have changed. Their balance systems are altered. Their muscles and bones have been stressed by microgravity, and now they must perform one of the hardest operations in spaceflight, landing on another planet. Mars landing is not simple. Mars has an atmosphere, but it is thin, too thin to slow a spacecraft easily like Earth's atmosphere, but thick enough to create dangerous heating and turbulence. Engineers often call it a difficult middle ground. The spacecraft must survive entry, descent, and landing with heat shields, parachutes, rockets, or other systems working in perfect sequence. If the landing fails, there is no rescue. If the habitat is damaged, the crew may have nowhere safe to live. If supplies are lost, the mission may become a survival emergency, and even after landing, Mars is not home. It is another hostile environment. The air is mostly carbon dioxide. The pressure is extremely low. The temperature is cold. Radiation is high. Dust can cover equipment. Solar power can be reduced by storms. Every walk outside requires a suit. Every breath requires machinery. So when people say, "We are going to Mars," it sounds like a destination. But for the crew, Mars is a chain of survival problems. Survive launch. Survive deep space. Survive radiation. Survive isolation. Survive landing. Survive the surface. Survive the return launch. Survive the trip home. Survive re-entry to Earth. The mission is not one risk. It is hundreds of risks connected together. That is what makes Mars so powerful and terrifying. It is close enough to dream about, but far enough to punish every mistake. It is reachable, but not forgiving. It is possible, but not easy. Mars is not science fiction anymore, but it is also not simple adventure. It is the first real test of whether humans can survive deep space for months and still function when the destination finally arrives. Part 17. The Mind in Deep Space. The body faces vacuum. The body faces radiation. The body faces low gravity, recycled air, artificial light, and machines that cannot fail. But the mind faces something just as dangerous: distance. Deep space does not only separate humans from Earth physically, it separates them emotionally, psychologically, socially, spiritually. On Earth, even when you are alone, the world surrounds you. You can step outside. You can hear traffic, wind, birds, rain, voices. You can walk away from a room. You can open a door. You can change your environment. You can see sky, buildings, trees, streets, people. In deep space, there is nowhere to go. The spacecraft is everything: bedroom, kitchen, bathroom, workplace, gym, laboratory, emergency shelter, prison, home. The same walls, the same sounds, the same faces, the same routines, day after day, month after month. There is no fresh air, no open window, no walking outside without a suit. No private escape into nature, no quick visit to family, no normal night out, no real separation between work and life. At first, the mission may feel exciting. The crew is highly trained. They know the purpose. They understand the risks. They have prepared for years. Cameras are watching. The world is inspired. But excitement is not a permanent mental state. After weeks, routine takes over. After months, the spacecraft becomes small. The same voice that was comforting may become irritating. The same habit from a crew member may become unbearable. A small disagreement can grow because there is no real space to cool down. No one can leave. No one can take a weekend away. The group must keep functioning because their lives depend on each other. Crew conflict in deep space is not just uncomfortable. It can become dangerous. A distracted crew makes mistakes. An angry crew communicates poorly. A depressed crew may lose motivation. A stressed crew may miss details. And in space, details matter. One valve, one checklist, one warning light, one forgotten tool, one delayed repair. A mental mistake can become a physical emergency. Then there is the communication delay. On the International Space Station, astronauts can often speak with people on Earth almost in real time. They can talk to family. They can receive support. They can see Earth through the window, huge and alive beneath them. On a Mars mission, Earth becomes distant. Messages take minutes to travel one way. At some distances, a question and answer can take more than 40 minutes round trip. That means no normal conversation. No quick emotional support, no immediate advice from mission control, no live argument, no live comfort, no real-time laughter with family. Communication becomes more like sending messages across an ocean that never ends. And then there is the view. At first, Earth is large and beautiful. Then it shrinks. Day by day it becomes smaller. The planet that held every human story, every ocean, every city, every memory, slowly turns into a bright dot behind the spacecraft. That image can be inspiring. It can also be terrifying, because the crew knows that everything they love is on that dot. And if something goes wrong, that dot cannot save them quickly. This is the psychological weight of deep space, knowing that home exists, but cannot reach you. Sleep can also become a problem. Spacecraft do not naturally provide sunrise, sunset, weather, or normal day-night rhythms. Light must be controlled artificially. Work schedules must be carefully planned. Noise from fans and systems may continue constantly. Stress can disturb rest, and poor sleep affects mood, memory, reaction time, and decision-making. On long missions, monotony becomes another enemy. Not every day is dramatic. Most days are maintenance, exercise, experiments, reports, repairs, cleaning, monitoring, checking supplies, and repeating routines. The mission is historic from Earth's view, but inside the spacecraft, life can become repetitive and confined. Humans need meaning to endure that. They need structure. They need trust. They need privacy. They need purpose. They need ways to handle fear without letting it spread. Because fear in deep space is different from fear on Earth. On Earth, fear often comes with options. Run, call for help, go outside, find a doctor, change location, wait for emergency services. In deep space, options are limited. If someone has a medical crisis, the crew handles it. If someone has a mental breakdown, the crew handles it. If someone becomes dangerous to themselves or others, the crew handles it. There is no ambulance, no police, no hospital. No family member arriving at the door, only the crew, the spacecraft, and delayed voices from Earth. That is why astronaut selection is so intense. Space agencies do not only choose people who are intelligent and physically fit. They need people who can work under stress, live in teams, manage emotions, follow procedures, communicate clearly, and remain stable in isolation. But even the best selection cannot remove all risk. Deep space is a psychological experiment we have not fully run yet. We have tested isolation on Earth. We have lived in space stations. We have simulated Mars habitats. But a real mission, millions of miles away with no quick return, is different. The body may survive the spacecraft. The question is whether the mind can survive the distance. Part 18. Zero gravity slowly rewrites the body. Vacuum can kill quickly. Radiation can damage silently, but weightlessness changes the body slowly, almost quietly, like a long experiment happening from the inside. Humans evolved under gravity. Every step you take on Earth tells your bones and muscles that they are needed. Your legs hold you up. Your spine supports your body. Your heart pumps blood upward against gravity. Your balance system uses gravity to understand direction. Your inner ear, eyes, muscles, bones, and brain all work together in a world where down always exists. In space, down disappears. At first, this seems magical. Astronauts float, objects hover, water forms spheres. A person can move across a module with a gentle push. Heavy equipment feels weightless, but the body does not see this as magic. The body sees it as a new environment and begins adapting. The problem is that some of those adaptations are harmful when astronauts need to return to gravity or land on another world. Start with muscles. On Earth, your muscles constantly work against gravity even when you are just standing. In weightlessness, many of those muscles are used far less. The legs, back, and core do not carry weight the same way. Over time, muscles weaken and shrink. This is called muscle atrophy. Astronauts fight it with exercise. They use resistance machines, treadmills with harnesses, cycling devices, and strict workout schedules. They may exercise for hours a day, but even with intense exercise, space still challenges the body. Then there are bones. Bones are living tissue. They respond to stress. On Earth, walking, standing, running, and lifting all signal bones to maintain strength. In microgravity, that mechanical loading decreases. The body begins breaking down bone faster than it rebuilds it. Calcium can leave the bones and enter the bloodstream. This means bone density can decrease. A weaker skeleton is not just a future problem. It can become a mission problem. If astronauts arrive on Mars after months in weightlessness, they may need to work on the surface, carry equipment, climb ladders, respond to emergencies, and survive landing stresses. Weakened bones and muscles make all of that harder. The cardiovascular system also changes. On Earth, gravity pulls blood downward. Your heart and blood vessels are adapted to move blood against that pull. In weightlessness, fluids shift upward toward the chest and head. Astronauts often experience puffy faces and thinner legs early in missions because body fluids redistribute. The body senses this fluid shift and may reduce blood volume over time. That works in space, but it can be a problem when returning to gravity. Some astronauts feel dizzy or faint after landing because the cardiovascular system must readapt to pulling blood upward again. Then there are vision issues. Some astronauts experience changes in eye shape and vision during long-duration missions. One suspected cause is fluid shifting toward the head, affecting pressure around the eyes and brain. This is a serious concern because clear vision is not optional in space. Astronauts must read displays, repair systems, conduct experiments, and respond to emergencies. The immune system may also change. Spaceflight can alter immune responses, stress hormones, inflammation, and microbial behavior. Microbes can behave differently in space. The closed spacecraft environment means bacteria, fungi, and human immune function all become part of mission health. Even balance changes. Your inner ear uses gravity to help understand orientation. In weightlessness, that system becomes confused at first. Many astronauts experience space motion sickness in the early days. Over time, the brain adapts to floating. But when returning to gravity, the brain must adapt again. Now think about Mars. Mars has gravity, but only about 38% of Earth's. That might help compared to zero gravity, but we do not know if it is enough to keep humans healthy long term. No one has lived for years in partial gravity. The Moon has about 1/6 Earth gravity. Mars has more, but still much less than Earth. This is one of the great unknowns. Can humans live healthily in 38% gravity? Can children develop normally there? Can bones stay strong? Can pregnancy happen safely? Can the heart and circulation remain healthy? Can people return to Earth after years on Mars, or would Earth gravity become too difficult? We do not know, and that uncertainty is huge. A Mars colony is often discussed like an engineering project: rockets, habitats, power, food, water. But biology may be one of the hardest parts. A habitat can be built, oxygen can be generated, water can be extracted. But if partial gravity slowly damages the human body, then long-term settlement becomes far more complicated. Artificial gravity is one possible solution. A spacecraft could rotate to create centrifugal force, giving the crew a gravity-like effect. But building large rotating spacecraft is difficult. It adds engineering complexity, structural stress, moving parts, and design challenges. We know the concept can work in physics, but practical human-rated systems are not yet common. So for now, astronauts rely on exercise, medical monitoring, nutrition, and mission limits. But deep space missions will push those limits. A 2-year Mars mission means the body must endure months of weightlessness, time in partial gravity, then months of weightlessness again, followed by return to Earth gravity. That is not just travel. It is a biological stress test. Space does not only threaten life through sudden disaster, it also reshapes the body quietly, day after day. And the body remembers Earth. Every bone, every muscle, every heartbeat, every drop of blood, all of it evolved under gravity. Take gravity away and the body begins asking a dangerous question. Do we still need to be built for Earth? Part 19. Why Mars is not a backup Earth yet. Mars is beautiful. That is part of the problem. Its red deserts, ancient river valleys, polar ice caps, massive volcanoes, and canyon systems make it feel almost familiar. From far away, Mars looks like a place humans could imagine walking across. It has landscapes, horizons, weather, seasons, a day length not too different from Earth's, so people call it humanity's backup planet. But that phrase is dangerous, because Mars is not a backup Earth. Not yet, not even close. Mars is a hostile world wearing the shape of a planet. Start with the air. Mars has an atmosphere, but it is extremely thin compared to Earth's. The surface pressure is less than 1% of Earth's sea level pressure. That means a human cannot breathe there. But more than that, a human cannot even stand outside unprotected. The low pressure itself is dangerous. The atmosphere is mostly carbon dioxide. There is no breathable oxygen in any useful amount, so every person on Mars would need a pressure suit outside and a pressurized habitat inside. The temperature is another problem. Mars is cold. Average temperatures are far below freezing. In some places and seasons, daytime temperatures can become less brutal, but nights can be extremely cold. Equipment must survive repeated heating and cooling cycles. Habitats must be insulated, water systems must be protected from freezing, suits must manage heat carefully. Then there is radiation. Mars does not have a global magnetic field like Earth. Its atmosphere is too thin to provide strong shielding. That means the surface receives much more radiation than Earth's surface. Cosmic rays and solar particles are a serious concern for long-term human presence. A person living on Mars would likely need habitats covered with thick layers of regolith, or built underground, or placed inside natural lava tubes if safe ones are found. The goal would be simple: put mass between humans and radiation. But living underground changes the dream. The popular image is people standing under glass domes, looking at the Martian sky. Reality may be more like buried tunnels, shielded habitats, and controlled interiors with no casual outdoor life. Then there is dust. Martian dust is not just dirt. It is fine, pervasive, and potentially harmful to machines and humans. It can cover solar panels, enter seals, scratch surfaces, cling to suits, and cause mechanical problems. Mars also has dust storms that can grow huge, sometimes affecting large parts of the planet. A major storm could reduce sunlight for weeks or months, making solar power less reliable. That means a Mars base may need nuclear power. Solar panels might help, but relying on them alone could be risky. Nuclear systems provide steady power, but they bring their own engineering, safety, political, and maintenance challenges. Water exists on Mars, mostly as ice, but accessing it is not trivial. You must locate it, mine it, melt it, filter it, store it, protect it from freezing. Use it for drinking, oxygen production, fuel production, agriculture, and radiation shielding. Water becomes one of the most valuable resources on the planet. Food is another challenge. You cannot simply plant crops in Martian soil and expect a farm. Martian regolith is not Earth soil. It lacks the rich organic ecosystem that plants depend on. It may contain chemical compounds that must be removed or managed. Crops would need controlled environments: pressure, warmth, water, nutrients, light, and protection from radiation. A greenhouse on Mars is not a normal greenhouse. It is a life support system for plants. And if crops fail, people go hungry. Then there is gravity. Mars gravity is only about 38% of Earth's. That sounds helpful compared to weightlessness, but no one knows what decades in Martian gravity would do to the human body. It may be enough to reduce some bone and muscle loss, or it may not be enough for long-term health. We simply do not have the data. Medical care would also be limited. If someone needs emergency surgery, there is no quick evacuation to Earth. If a child is born, doctors would be facing unknown developmental risks. If an infection spreads, the closed habitat environment becomes dangerous. If mental health declines, the entire crew may be affected. This is why backup Earth is misleading. A real backup must support civilization independently. Mars cannot do that yet. A small Mars base would depend heavily on Earth for equipment, spare parts, medicine, advanced electronics, tools, replacement systems, and possibly food. If Earth stopped sending supplies, the base might struggle or fail. That is not a backup civilization. That is a distant outpost. For Mars to become a true second home, humans would need industry there: mining, manufacturing, energy production, agriculture, medicine, repair facilities, education, governance, transportation, construction, recycling. Birth, death, culture, law, and stability. That is not impossible, but it is enormous. Mars may be the next great frontier, but it is not waiting as a ready-made refuge. It is not Earth with red sand. It is a frozen, low-pressure, radioactive desert where survival depends on machines. And that matters because dreams are powerful, but survival is technical. If humans go to Mars, they must go with clear eyes. Not because it is easy, not because it is safe, not because it is already a backup, but because building a human future there would be one of the hardest things our species has ever attempted. Part 20. The colony problem. Survival is not the same as civilization. There is a huge difference between reaching Mars and living on Mars, and there is an even bigger difference between living on Mars and building a civilization there. A spacecraft landing successfully is not a colony. A habitat with a few astronauts is not a city. A flag in the soil is not independence. The first human base on Mars, if it happens, will probably be one of the most fragile homes ever built. Every breath inside it will depend on machines. Every drop of water will need to be collected, cleaned, stored, and protected. Every meal will come from supplies, controlled farming systems, or carefully managed production. Every repair will matter. Every failure will be serious. That is survival. Civilization is something much larger. A civilization must be able to continue. It must replace broken parts. It must produce tools. It must train new people. It must heal the sick. It must grow food reliably. It must manage conflict. It must survive accidents. It must create culture, education, law, memory, and purpose. It must not collapse if one shipment from Earth fails. This is the real colony problem. Many people imagine Mars settlement as if it were like humans crossing oceans or settling new continents, but that comparison is misleading. On Earth, even the harshest frontiers still had air, gravity, pressure, natural water cycles, and a biosphere. People could hunt, farm, burn wood, breathe freely, and build with local materials. Mars gives none of that easily. You cannot breathe the air. You cannot drink untreated water from rivers. You cannot grow crops outdoors. You cannot walk outside without a suit. You cannot use a simple campfire for warmth. You cannot rely on natural weather to support life. A Mars colony would be more like a submarine, a polar research station, a nuclear facility, and a space station combined, but farther away than any of them. The first challenge is spare parts. Machines break, pumps fail, filters clog, seals degrade, electronics burn out, motors wear down, sensors drift out of calibration. On Earth, a broken part can be ordered, shipped, replaced, or manufactured in a nearby industrial system. On Mars, every missing part becomes a serious question. Did we bring a spare? Can we repair the old one? Can we manufacture a replacement? Do we have the raw materials? Do we have the tools? Do we have the power? Do we have the expertise? If the answer is no, a small failure can become a large crisis. That means a serious Mars colony needs manufacturing, not just 3D printers for simple plastic parts. It needs the ability to process metals, produce electronics, repair circuits, make pressure seals, fabricate tools, manufacture building materials, and maintain complex life support systems. That requires industry. Industry requires power. Power requires infrastructure. Infrastructure requires more machines. More machines require more maintenance. The chain keeps growing. Then there is food. For a small crew, food can be brought from Earth. For a colony, that is not enough. A settlement needs agriculture, but agriculture on Mars requires pressurized growing spaces, controlled lighting, nutrients, water recycling, temperature regulation, pollination systems or human intervention, pest control, microbial management, and backup crops in case one system fails. A failed harvest on Earth is bad. A failed harvest on Mars could be fatal. Then there is medicine. A colony cannot rely only on basic first aid. People will get injured. People will develop infections. Bones may break. Appendixes may burst. Dental problems will happen. Pregnancies may happen. Mental health crises may happen. Chronic diseases may appear. Surgeries may be needed. That means a colony needs doctors, equipment, medicine production, or large medical stores, sterilization systems, diagnostic tools, and training for emergencies. But medicine expires. Equipment breaks. Specialists are limited, and Earth is months away. Governance is another problem. In a tiny base, mission rules may work. In a growing settlement, politics appears. Who decides how oxygen is rationed during a crisis? Who owns the habitat? Who controls food production? What happens if someone refuses duties? What happens if people disagree with Earth-based authorities? What rights do Mars-born children have? What laws apply? A colony cannot survive on engineering alone. It needs social stability, and social stability is not automatic in a sealed habitat under stress. Conflict on Mars would be dangerous because everyone depends on shared systems. You cannot simply move to another city. You cannot walk away from the air supply. You cannot ignore the water recycler. The entire colony is a connected survival machine. That means trust becomes infrastructure, culture becomes infrastructure, rules become infrastructure, mental health becomes infrastructure. Education is also essential. If a colony lasts generations, it must teach children not only language, history, and science, but the technical skills required to keep the colony alive. Every generation must understand life support, agriculture, repair, medicine, emergency response, and the reality of Mars. A civilization must reproduce knowledge, not just people. This is why the first Mars settlement may be historic, but still not self-sufficient. It may depend on Earth for decades, maybe longer. Supplies, experts, advanced equipment, medicines, computers, replacement parts, all may need to come from Earth. That dependence matters, because if Mars is supposed to be a backup for humanity, it must eventually survive without Earth. If Earth suffers a disaster and Mars cannot continue alone, then Mars is not a backup civilization. It is another victim waiting for the supply chain to fail. That is the real bar: self-sufficiency. A Mars colony must become capable of producing what it needs, repairing what it uses, growing its population safely, and surviving without constant help. That is far harder than landing rockets. Rockets create access. Civilization requires continuity. A flag on Mars would prove we can arrive. A base on Mars would prove we can survive. But a true city on Mars would prove something much deeper: that humans can carry Earth's life support logic into a dead world and make it last. And that may be one of the hardest challenges in human history. Part 21. The outer solar system. Even worse than Mars. Mars is already brutal. It is cold, dry, radioactive, low pressure, and almost completely hostile to human life. But Mars is still close compared to the outer solar system. It still gets decent sunlight. It still has a day-night rhythm that feels somewhat familiar. It is still a world humans can imagine reaching with technology we are slowly developing. But beyond Mars, the solar system becomes something else. Darker, colder, slower. More distant, more alien. When people talk about the moons of Jupiter and Saturn, they often sound excited. Europa may have an ocean beneath its ice. Enceladus sprays water vapor into space. Titan has lakes, rivers, weather, and a thick atmosphere. These places are scientifically fascinating. They may be some of the best locations to search for life beyond Earth, but for humans, they are nightmares. Start with distance. Mars is difficult because it takes months to reach. Jupiter can take years. Saturn takes even longer. That means longer time in deep space, more radiation exposure, more equipment wear, more psychological isolation, more food and water requirements, and more chances for something to fail before arrival. Every extra month in space increases risk. Now imagine a mission not lasting 2 or 3 years, but 5, 7, 10 or more. That is not a normal expedition. That is a life chapter. The crew would spend years inside a spacecraft before even beginning serious surface operations. By the time they arrive, the spacecraft has already had years to degrade. Pumps have been running, filters have been used, seals have aged. Electronics have taken radiation hits. Humans have lived in confinement for a dangerously long time. Then comes the environment. Jupiter is surrounded by powerful radiation belts. Its magnetic field traps charge particles and accelerates them. Around some of its moons, especially Europa, radiation can be intense enough to damage electronics and kill unprotected humans quickly. A person could not simply walk on Europa's surface in a normal suit and expect safety. The radiation environment would demand serious shielding, likely underground or under thick ice. Europa is beautiful in imagination, a world of ice covering a hidden ocean, but on the surface, it is a frozen radiation zone. The ice is extremely cold. The sunlight is weak. The sky is dominated by Jupiter, huge and terrifying. The surface may be cracked, jagged, unstable, and constantly reshaped by tidal forces. Any human outpost would need heavy shielding, reliable nuclear power, and protection from both radiation and cold. Then there is Enceladus, Saturn's icy moon. It is smaller, farther, colder, and famous for plumes of water vapor erupting from cracks near its south pole. Scientists love it because those plumes may allow sampling of subsurface ocean material without drilling through miles of ice. But for humans, Enceladus is not friendly. The sunlight near Saturn is weak. Solar power becomes much less practical. The temperature is extreme. The gravity is tiny. A human base would need artificial systems for almost everything: power, heat, pressure, radiation protection, food, water processing, and medical care. Then Titan. Titan is often described as one of the more Earth-like places because it has a thick atmosphere, weather, clouds, rivers, lakes, and seas. But those lakes are not water. They are liquid methane and ethane. Titan is so cold that water behaves like rock. Its atmosphere is thick but unbreathable. Its surface temperature is around -179°, or about -290°. That is beyond anything human biology can tolerate. Metal, plastics, seals, electronics, and machinery would all have to be designed for a cryogenic world. Titan's thick atmosphere could help with radiation shielding, and its lower gravity and atmospheric density might make flight easier for robotic aircraft. But that does not make it comfortable for humans. A person standing outside would still need a sealed heated suit, oxygen, pressure management, and protection from extreme cold. On Mars, the challenge is surviving a dead desert. In the outer solar system, the challenge is surviving alien worlds where sunlight is weak, rescue is impossible, and the environment is so extreme that every piece of equipment must become part of the life support chain. Power becomes a central problem. Near Earth and Mars, solar panels can be useful. Farther out, sunlight fades. At Jupiter, sunlight is much weaker than at Earth. At Saturn, weaker still. A serious human mission would likely need nuclear reactors, not tiny batteries, not backup generators. Real, long-duration power systems capable of keeping habitats warm, running life support, powering drills, operating labs, charging rovers, and maintaining communication. Without power, the base dies. Heat stops. Air stops, water systems freeze, electronics fail, lights go out, and the crew is stranded far from Earth. Communication delays also become worse. Messages to Jupiter and Saturn take much longer than messages to Mars. Real-time help is impossible. Mission control becomes a distant advisor, not an immediate partner. The crew must be independent. They must repair, diagnose, improvise, and survive without waiting for Earth. That is why the outer solar system is not simply the next step after Mars. It is a completely different scale of difficulty. Mars is hard. Jupiter's moons are harsher. Saturn's moons are farther. And every kilometer away from Earth makes rescue less realistic. These worlds may hold secrets about life, chemistry, oceans, and planetary history. Robots should explore them. Probes should study them. Landers and drills may one day search their ice and atmosphere. But humans living there is another matter. That would require technology far beyond what we currently use. Stronger radiation protection, reliable nuclear power, closed-loop life support for many years, advanced medical autonomy, psychological resilience for extreme isolation, and spacecraft that can function without major failure for a decade or more. The outer solar system is not impossible forever, but it is not waiting politely for us. It is cold, distant, radioactive, and slow. And if Mars is the first serious test of human deep space survival, the outer solar system is the final exam. Part 22. Interstellar Space. The True Void. Deep space is hostile, but interstellar space is something beyond hostile. It is the true void between stars, no planet nearby, no warm sunlight, no quick communication, no rescue, no destination visible as anything more than a distant point of light. When people imagine traveling to another star, they usually imagine speed, a futuristic ship, a dramatic countdown, stars stretching past the window, a new world waiting at the other end. But reality is not like that. Reality begins with distance. The nearest known star system to our Sun is Alpha Centauri, with Proxima Centauri as the closest star in that system. It is about 4.4 light-years away. A light-year sounds poetic, but it is a measurement of distance, how far light travels in 1 year. Light moves at about 300,000 kilometers per second, and even at that speed, it takes more than 4 years to reach the nearest star. Now compare that with our spacecraft. Voyager 1, one of humanity's fastest and farthest spacecraft, would take tens of thousands of years to reach the distance of another star if it were aimed correctly. Tens of thousands of years, that is not a mission. That is longer than human civilization as we know it. So if humans ever want to travel between stars, we need propulsion far beyond ordinary rockets. Chemical rockets are powerful enough to launch from Earth and move through the solar system, but they are nowhere near enough for human interstellar travel. The fuel requirements become absurd. the timescales become impossible. The spacecraft would need to carry life support for generations unless speed improves dramatically. Possible future concepts exist: fusion rockets, antimatter propulsion, nuclear pulse propulsion, laser-pushed light sails, generation ships, suspended animation. Each sounds exciting. Each also carries enormous problems. Fusion rockets would use the energy of nuclear fusion, the same type of process that powers stars. In theory, fusion propulsion could be far more efficient than chemical rockets. But building a reliable fusion reactor is already one of the hardest engineering challenges on Earth. Building one that works as a spacecraft engine for decades is far beyond current capability. Antimatter is even more powerful in theory. Matter and antimatter annihilate when they meet, converting mass into energy with incredible efficiency. But producing antimatter is extremely difficult. Storing it safely is even harder. A tiny containment failure could release catastrophic energy. We have no practical antimatter engine and no affordable way to produce the amounts needed. Laser sails are fascinating. A very light sail could be pushed by powerful lasers from the solar system. This might accelerate tiny probes to a significant fraction of light speed. But humans are not tiny probes. Humans need shielding, oxygen, water, food, living space, medical supplies, power systems, and protection. Add all of that mass, and the sail problem becomes far harder. And even if you accelerate toward another star, you must stop. That is the part many people forget. A spacecraft traveling at high speed cannot simply arrive and park. It must slow down. Slowing down requires energy, fuel, or some interaction with the destination system. If you cannot slow down, you only fly past the star at incredible speed, collecting a brief glimpse before disappearing forever into darkness. For a robotic probe, a flyby might be acceptable. For humans, it is not. No crew would spend decades traveling just to rush past the destination in hours. So interstellar travel is not one problem. It is two. How do you accelerate, and how do you decelerate? Then comes the environment itself. Interstellar space has almost no matter, but it is not completely empty. There are atoms, dust grains, magnetic fields, radiation, and cosmic rays. At ordinary speeds, tiny particles are not a major issue. But at a significant fraction of light speed, even a small dust grain becomes dangerous. It can strike with enormous energy. A spacecraft traveling between stars would need shielding not just from radiation, but from impacts with tiny particles. Again, shielding means mass. More mass means harder acceleration. Harder acceleration means more energy. The problems keep connecting. Radiation is also severe. Far from planets and away from strong protective magnetic fields, the crew would face galactic cosmic rays for decades. A ship would need thick shielding, perhaps water tanks or hydrogen-rich materials around crew areas. But for a decades-long mission, the shielding must be serious. Then there is power. In interstellar space, solar panels are nearly useless. The sun becomes just another star behind you. The destination star is still too far ahead. A ship must carry its own power source, likely nuclear, and not a small power source. A human habitat needs energy for heat, lighting, life support, recycling, agriculture or food systems, computing, communication, medical equipment, repairs, and possibly propulsion. That power system must work not for days or months, but for decades, maybe longer, with limited maintenance, far from Earth. If it fails, the mission dies. Now think about the humans. A trip to the nearest star, even at a speed far beyond anything we have achieved, might take decades. At slower speeds, it could take centuries or thousands of years. That means either the original crew must survive an entire lifetime in transit, or multiple generations must be born, live, reproduce, and die on the ship. That is the generation ship idea. It sounds romantic until you think about it carefully. The first crew chooses the mission. Their children do not. Their grandchildren do not. People would be born inside a spacecraft with no choice to leave, no planet, no open sky, no ocean, no forest, no natural horizon. Their entire world would be corridors, artificial light, recycled air, controlled food, mission rules, and stories about a destination they may never see. How do you maintain purpose across generations? How do you prevent social collapse? How do you avoid inbreeding in a limited population? How do you educate children for a world they have never seen? How do you handle rebellion, depression, crime, leadership conflict, resource shortages, or loss of belief in the mission? A generation ship is not just a spacecraft. It is a civilization inside a machine. And if that machine fails, everyone dies. This is why interstellar travel remains far beyond us. Not because humans lack imagination, But because physics is severe, distance is severe, energy is severe, biology is severe, society is severe, interstellar space is not an ocean waiting for ships. It is an abyss measured in light years, a place where even light takes years to cross, where rescue is impossible, where a message home may take years, where a spacecraft becomes completely alone. And that is the deepest truth. Deep space is hostile because it attacks the body. Interstellar space is terrifying because it attacks meaning. It forces humans to ask whether survival is still survival if generations live and die inside a machine before reaching a world they never chose. It is the true void. Not empty, not peaceful, but vast beyond human instinct. And if humanity ever crosses it, that will not be a normal journey. It will be one of the most extreme acts of faith, engineering, sacrifice, and risk our species has ever attempted. Part 23. The ethics of sending humans into the void. After understanding the danger, one question becomes impossible to avoid. Should we send humans into deep space at all? Not can we. Should we? Because there is a difference between what technology can attempt and what humanity should choose. Robots can go where humans cannot. Robotic probes can survive radiation, cold, vacuum, and long isolation without oxygen, food, sleep, or emotional support. A rover does not panic. A satellite does not develop depression. A probe does not need water recycling, medical care, or a pressurized cabin. When a robotic mission fails, it is tragic for science and expensive for the budget. But no family loses a living person. So why send humans? This question matters because human spaceflight is not just exploration. It is risk accepted by real people. Astronauts are not symbols only. They are bodies, minds, families, histories, fears, and dreams. When we send them beyond Earth, we ask them to trust machines against an environment that kills quickly. That requires justification. Some argue that humans are better explorers than robots. A trained geologist on Mars could make decisions faster than a rover controlled with communication delay. A human can notice unexpected details, improvise repairs, adapt to surprises, and understand context in ways machines still struggle with. That is true. Humans are flexible. Humans are creative. Humans can respond to the unknown. But the cost of keeping humans alive is enormous. Every breath requires systems. Every meal requires mass. Every drop of water must be carried or recycled. Every human mission requires shielding, safety, waste management, medical planning, emergency return possibilities, and life support. Robots are simpler, so the argument for human exploration cannot be only efficiency. It must include something deeper, inspiration, identity, the future, the human desire to see with our own eyes, touch with our own hands, and carry consciousness into places where no living mind has been. That is powerful. But it still does not erase the ethical difficulty. How much risk is acceptable? If astronauts volunteer, is that enough? Adults can choose dangerous missions. Test pilots, explorers, soldiers, deep-sea divers, and rescue workers have always taken risks. If a trained astronaut understands the danger and chooses to go, many people would say that choice should be respected. But deep space missions complicate consent. What about Mars settlers who have children? What about people born off Earth? What about generationships? A child born on Mars does not choose low gravity, radiation risk, closed habitats, limited medical care, and dependence on life support systems. A child born on a generation ship does not choose to spend life between stars. They inherit a mission created by ancestors. Is that fair? On Earth, no child chooses where they are born either. People are born into deserts, islands, cities, poverty, wealth, war zones, safe countries, and unstable societies. But deep space adds a unique element: physical confinement with no natural environment and no easy exit. A child on Earth can at least breathe the atmosphere. A child in deep space depends on machines every second. That raises hard questions. Do future generations have the right to an open planet? Do they have the right to refuse a mission? What happens if a generation ship population decides it no longer wants to continue? Can they turn back? Can they survive without completing the journey? Who has authority across generations? The original planners? The current crew? A constitution written before some passengers were born? These are not just science fiction questions. They are ethical problems that would become real if humans attempt permanent settlement beyond Earth. There is also the question of priorities. Should humanity spend massive resources trying to leave Earth while problems remain here? Climate stress, poverty, war, disease. environmental damage, food insecurity, political instability. Some people argue that space exploration distracts from Earth's urgent problems. Others argue that space technology helps Earth through satellites, climate monitoring, communications, materials science, and inspiration. They also argue that becoming multiplanetary may protect humanity from extinction-level events. Both sides have a point. We should not use space as an excuse to abandon Earth, but we also should not stop exploring because Earth has problems. The real ethical path may be balance, protect Earth while exploring carefully, honestly, and responsibly. Another issue is planetary protection. If Mars or Europa has native microbial life, do humans have the right to contaminate it? Our bodies carry microbes. Our machines carry microbes. Even with sterilization, perfect cleanliness is nearly impossible. A human mission could introduce Earth organisms to another world and confuse or damage the very alien biology we hope to discover. If life exists elsewhere, even simple microbial life, it may represent a second origin of biology. That would be one of the greatest discoveries in history. We must be careful not to destroy the evidence before understanding it. Then there is inequality. Who gets to go? Who benefits? Will space become a shared human frontier or only a playground for powerful nations and wealthy corporations? Will resources from space help humanity broadly or create new forms of control and competition? Will off-world settlements reproduce Earth's injustices under even harsher conditions? Technology does not automatically create wisdom. Humans bring their politics with them, their conflicts, their ambitions. They're mistakes, so sending humans into the void is not only a technical challenge, it is a moral one. We must ask not just how to survive, but what kind of humans we want to be when we arrive. Because if we carry only our machines into space, we may survive physically. But if we carry our worst instincts without reflection, we may build fragile new worlds with the same old failures. Deep Space Force's honesty. It strips away romance and asks, what is worth risking human life for? What do we owe future generations? Can exploration be brave without being reckless? Can settlement be ambitious without being exploitative? Can humanity reach outward without forgetting the planet that made us? There may not be easy answers, but any serious future in space must face these questions before the rockets launch. Part 24, Why We Still Go. After all of this, after vacuum, radiation, isolation, fragile spacecraft, failing suits, weak gravity, Mars hazards, outer solar darkness, and interstellar distance, a simple question remains. Why go? Why leave Earth at all? Why step into an environment that seems designed to reject us? Why risk human lives when robots can explore more safely? Why spend generations solving problems that Earth already solved naturally? The answer is not simple, but it is deeply human. We go because humans have always looked beyond the edge of safety, not because danger is attractive by itself, not because risk is good for its own sake, but because curiosity is one of the strongest forces in our species. We are not satisfied with only existing. We want to understand where we are, what surrounds us, how reality works, and whether we are alone. The night sky has always been more than decoration. It has been a question. Ancient people looked upward and saw gods, omens, patterns, seasons, and mystery. Later, we built telescopes and discovered planets, moons, nebulae, galaxies, and an expanding universe. Then we built rockets and sent machines beyond Earth. Then humans followed. Every step revealed something humbling. Earth is not the center. The sun is one star among many. Our galaxy is one galaxy among billions. The universe is older, larger, stranger, and more violent than human intuition ever imagined. And still, here we are, able to understand pieces of it. That alone is extraordinary. We go to space because exploration changes us. It forces new technology. It forces cooperation. It forces precision. It makes us solve hard problems that later help life on Earth. Satellites improve weather prediction, disaster response, navigation, communication, agriculture, climate monitoring, and science. Space missions push engineering in ways that ripple back into ordinary life. But beyond practical benefits, space gives perspective. When astronauts see Earth from orbit, many describe a shift in awareness. Borders disappear. The planet looks small, fragile, alive. A thin atmosphere surrounds everything we know. The darkness beyond it is immense. That view does not solve human conflict, but it can change how people think about home. Space makes Earth visible as a single system. That matters. We also go because survival may eventually require it. Earth is safe compared to space, but it is not permanently safe. Asteroids exist. Supervolcanoes exist. Climate instability is possible. Nuclear war is possible. Engineered pandemics are possible. Future technologies may create risks we do not yet understand. And over very long timescales, Earth itself will become uninhabitable as the sun changes. None of this means we should panic. It means that a species with long-term intelligence should think beyond one planet. A civilization living only on one world is vulnerable. A civilization spread across multiple worlds has more chances to continue. That does not make space settlement easy. It does not make Mars ready. It does not erase ethical questions, but it explains why the dream persists. We go because life wants continuity. But perhaps the most important reason is this. We go because humans are meaning-making creatures. A purely practical species might stay home forever. It might say the risk is too high, the cost too large, the void too hostile. But humans do not live by practicality alone. We build cathedrals. We write music. We climb mountains. We cross oceans. We study fossils. We search the deep sea. We send messages into space knowing no one may answer. We do these things because existence is not only about survival, it is also about wonder. Space exploration is dangerous, but danger does not automatically make something meaningless. In fact, understanding the danger can make the achievement more powerful. An astronaut stepping outside a spacecraft is not just floating. They are entering an environment where a human body cannot survive naturally for even minutes. They are trusting thousands of people, millions of parts, decades of science, and the discipline of engineering. They are carrying human curiosity into a place that has no reason to welcome them. That is not ordinary bravery. That is civilization-level courage. But courage must be honest. We should not pretend space is easy. We should not sell Mars like a simple real estate project. We should not describe interstellar travel like a vacation. We should not turn astronauts into cartoon heroes who defeat physics through confidence. Physics does not care about confidence. That is exactly why exploration must be respected. Real space exploration is not fantasy. It is not casual. It is difficult, expensive, dangerous, slow, and unforgiving. And still, it matters. Because every time humans explore, we expand the boundary of what our minds can hold. We learn not only about the universe, but about ourselves. We discover what we can build, what we can endure, what we value, and what we are willing to risk for knowledge. The goal should not be escape from Earth. The goal should be maturity. A mature, spacefaring civilization would protect Earth more, not less. It would understand that our home planet is not disposable. It would explore with humility, not arrogance. It would send humans when humans add meaning or capability, and robots when robots make more sense. It would treat other worlds carefully. It would think about future generations before creating irreversible missions. We still go because the universe is too important to ignore. But we go best when we go with respect. Respect for the danger. Respect for the science. Respect for life. Respect for Earth. Because the truth is not that space is too dangerous to explore. The truth is that space is so dangerous that exploration becomes even more extraordinary. Part 25. Earth, the only spaceship that already works. After looking into deep space, Mars, the outer planets, and the void between stars, one truth becomes impossible to ignore. Earth is not just our home. Earth is the only spaceship we already have that works perfectly enough to keep billions alive without asking them to understand the machinery. Think about that. A spacecraft must manage oxygen. Earth does it through plants, oceans, atmosphere, and cycles built over unimaginable time. A spacecraft must recycle water. Earth does it through evaporation, clouds, rain, rivers, ice, groundwater, and oceans. A spacecraft must regulate temperature. Earth does it through atmosphere, greenhouse gases, oceans, winds, clouds, ice, land, and sunlight balance. A spacecraft must shield radiation. Earth does it with magnetic field, atmosphere, and ozone. A spacecraft must provide food. Earth does it through soil, microbes, sunlight, rain, pollination, ecosystems, and farming. A spacecraft must manage waste. Earth does it through decomposition, bacteria, fungi, insects, soil chemistry, and biological cycles. A spacecraft must maintain pressure. Earth does it with gravity holding atmosphere around the planet. Every system engineers struggle to create in space already exists here in a natural form, and we often treat it as ordinary. That may be the greatest mistake. Because Earth's life support system is not guaranteed. It is strong, but not invincible. It can absorb damage, but not infinite damage. Atmosphere can be changed. Oceans can be polluted. Climate systems can be disturbed. Species can vanish. Soil can degrade. Forests can be destroyed. Water cycles can shift. Earth is forgiving compared to Mars, but it is not indestructible. When people dream of leaving Earth, sometimes they speak as if another home is waiting nearby. But there is no easy replacement. Mars would require sealed habitats, pressure systems, radiation shielding, artificial agriculture, constant repair, and extreme discipline. The Moon is airless, dry, and exposed. Europa is frozen and radioactive. Titan is cryogenic and unbreathable. Interstellar planets are unreachable with current technology. Earth is not one option among many. Earth is the only known world where a human can stand outside, take off a helmet, breathe, feel wind, drink water, grow food, hear birds, watch clouds, and survive without a machine wrapped around the body. That is not sentimental. That is biological fact. We are Earth organisms. Our lungs are Earth lungs. Our blood is Earth blood. Our bones are Earth bones. Our circadian rhythms, senses, digestion, immune system, psychology, and chemistry all formed inside this planet's conditions. Even our idea of comfort is Earth-based. Warm sunlight, fresh air, flowing water, open sky, natural gravity, changing seasons, living landscapes. In deep space, none of that comes free. Everything must be manufactured. Even silence is different there. On Earth, silence still has life inside it. Wind, distant animals. Leaves, insects. Water, human movement. In space, silence is absence. No air, no sound, no life unless we bring it. That is why understanding space should not make us hate space. It should make us love Earth more intelligently. Space is magnificent. The stars are real. The galaxies are real. Other worlds are real. Exploration is worth doing, but Earth is not a prison to escape. Earth is the rare oasis that made exploration possible in the first place. We do not protect Earth because we are afraid of space. We protect Earth because we understand space. We understand that the universe is mostly not like this. Most places do not have breathable air. Most places do not have liquid water on the surface. Most places do not have mild temperatures. Most places do not have soil full of life. Most places do not have a sky that protects instead of kills. Most places do not have rain. Most places do not have oceans. Most places do not have forests. Most places do not have anything that cares whether humans live or die. Earth does not care in a conscious way either, but its systems happen to support us, and that makes it precious beyond measure. If humanity becomes spacefaring, Earth will still matter. It will be the origin, the cradle, the biological reference point, the place every human story began. Even if cities rise on Mars one day, even if ships cross deep space, even if humans build habitats around other worlds, Earth will remain the planet that taught our species how to live. And perhaps the best reason to explore space is not to abandon Earth, but to finally see it clearly. To understand that the atmosphere is thin, that oceans are rare, that life is fragile, that our world is not automatically replaceable, that every breath is part of a planetary miracle. When you look at Earth from space, it does not look huge. It looks delicate, a blue and white sphere surrounded by darkness. No walls, no visible shield, just a thin atmosphere separating every living thing we know from the vacuum outside. That thin shell is why we are here. That thin shell is why language exists, why cities exist, why history exists, why music exists, why anyone can look up at the stars and wonder. Deep space teaches one lesson more clearly than almost anything else. Earth is not ordinary. Earth is the miracle we keep standing on. Part 26, final ending, physics does not negotiate. So now, when we return to the original question, why no one can survive deep space without extraordinary protection, the answer is not mysterious anymore. It is pressure. It is oxygen. It is radiation. It is temperature. It is biology. It is distance. It is engineering. It is physics. And physics does not negotiate. A human body exposed to deep space is not entering a dramatic movie scene. It is entering an environment where the rules of survival disappear almost instantly. The body looks for air, but there is none. The lungs depend on pressure, but pressure is gone. The blood depends on stable gas behavior, but dissolved gases begin to betray it. Moisture depends on atmospheric pressure, but exposed liquid starts vaporizing. The brain depends on oxygen, but oxygen delivery collapses in seconds. There is no villain, no intention, no anger. Just the universe behaving exactly as it always has. That may be the most terrifying part. Deep space is not trying to kill you. It simply does not include you. It has no natural place for lungs, no natural place for warm blood, no natural place for unshielded eyes, no natural place for skin, speech, breath, or heartbeat. The human body is a masterpiece of Earth biology, but outside Earth's protection, it becomes fragile very quickly. That does not make humans weak. It makes Earth special. Every astronaut who enters space survives because a small artificial Earth goes with them. A spacecraft cabin, a pressure suit, oxygen systems, carbon dioxide scrubbers, cooling loops, radiation shelters, water recyclers, heat radiators, alarms, valves, pumps, sensors, checklists, teams of engineers, decades of testing. Spaceflight is not humans conquering space by strength. It is humans surviving space through precision. That is far more impressive, because the environment is not helping. When an astronaut performs a spacewalk, the universe outside the visor is instantly fatal. The calm voice on the radio hides the reality that a seal, a glove, a cooling system, or a pressure layer is holding back vacuum. Every movement is taking place inside a machine that must continue working. When a spacecraft travels beyond Earth, it becomes a tiny island of order in a cosmic ocean of danger. Inside, there is breathable air, warmth, light, water, and human thought. Outside, there is vacuum, radiation, micrometeoroids, and silence. That contrast is almost impossible to fully understand. A few centimeters of wall can separate conversation from death. A few millimeters of visor can separate eyesight from radiation. A pressure seal can separate a living astronaut from a body in vacuum. A working pump can separate comfort from overheating. A functioning scrubber can separate normal breathing from carbon dioxide poisoning. Space is not forgiving because space has no reason to be, and yet we go. That is the contradiction at the heart of human exploration. We are fragile but curious, limited but imaginative, earthborn but star-facing. We know deep space is dangerous, and still we build machines to enter it. We know Mars is hostile, and still we plan missions. We know interstellar travel is beyond us today, and still we study the physics. We know the universe is vast beyond instinct, and still we ask what lies beyond the next horizon. That curiosity is one of humanity's greatest strengths, but it must be paired with humility. The stars are beautiful, but they are not gentle. Mars is inspiring, but it is not a second Earth yet. The outer solar system is fascinating, but it is not waiting as a home. Interstellar space is magnificent, but it is not an ocean we can casually cross. Every step outward must be made with respect for reality, not fantasy, not hype, not the illusion that courage can replace engineering. Courage matters, but courage does not create pressure. Hope matters, but hope does not block radiation. Dreams matter, but dreams do not recycle oxygen. If humans are going to survive beyond Earth, we must solve problems at the level of physics, biology, psychology, and civilization. We must build systems that can run for years, habitats that can protect against radiation, suits that can survive failure conditions, spacecraft that can repair themselves or be repaired by crews far from home, life support that can recycle nearly everything, medical systems that can function without hospitals, social systems that can keep small groups stable in extreme isolation. This is not impossible, but it is enormous, and that is why deep space deserves respect, not fear that paralyzes us, respect that makes us serious. Because space exploration is not less amazing when we understand the danger, it is more amazing. A rocket launch becomes more than spectacle. It becomes the beginning of a fight against gravity, vacuum, radiation, and distance. A spacewalk becomes more than a beautiful video. It becomes a human being operating inside a life support machine in a place where one serious failure could end everything. A Mars mission becomes more than a headline. It becomes a multi-year test of engineering, biology, discipline, teamwork, and courage. And Earth becomes more than background. Earth becomes the reason any of this is possible. The next time you look up at the night sky, remember both truths. Remember the beauty, the stars, the galaxies, the planets, the mystery, the possibility that somewhere out there other worlds may exist with oceans, atmospheres, maybe even life. But also remember the danger, the vacuum, the radiation, the temperature extremes. The distance is so vast that light itself takes years to cross them. The silence that is not peaceful but absolute. The emptiness that does not hate us but also does not protect us. That is the real universe, magnificent and merciless. And between us and that universe is a thin shell of atmosphere, a magnetic field, a warm planet, liquid water, and a biosphere that has carried life for billions of years. We should explore. We should learn. We should build. We should reach. But we should never forget what keeps us alive, because humans were not born in the void. We were born under a sky that protects us, on a world that gives us pressure, water, warmth, air, gravity, and life. Deep space is not impossible to enter, but it is impossible to survive casually. There is no casual breath beyond Earth, no casual step on Mars, no casual journey between stars. Every breath out there must be engineered. Every day must be defended. Every life must be protected by systems that cannot afford to fail. And that is the final truth. The universe is not cruel. It is not kind either. It is simply real. And reality has rules. In deep space, those rules are written in vacuum, radiation, cold, distance, and silence. You can dream beyond Earth. You can build beyond Earth. You can even live beyond Earth one day. But you cannot negotiate with the laws that govern the void. You either understand them, or they end you. That is why no human survives deep space without protection. Not because humans lack courage. Not because the dream is foolish. But because deep space is the purest reminder that physics does not bend for life. Life survives only when it builds a shield strong enough to stand between itself and the universe. And for now, the greatest shield we have is still here, Earth. Our first spacecraft, our only natural home. The one world where we can breathe without machines. The one world where the sky itself holds back the void. And maybe, before we rush toward the stars, we should look once more at the planet beneath our feet and understand what it really is. Not ordinary, not replaceable, not guaranteed. A rare blue shelter in a universe that does not negotiate.